the StatNet suite. If you think about what's changed in networks for the last 30 years, probably the single biggest change has been the statistical turn in networks, to be able to model them in tools that smell a little like the sort of tools that we're used to using in STEM and social science, and that's his fault. So it's really he's been a big fan of this, a big supporter of this workshop for all the years we've done it, and it's really great to have you here. Thanks, Mark.
All right, well, thank you very much, and thanks everyone for getting up in the morning. If you're not a morning person, as I am not a morning person, I'm aware of the sacrifice you're making to look at some slides and have some interaction. And of course, I also want to thank Jim, and I want to thank the rest of the folks here, all the staff and the people at Duke for doing this effort, because as anyone who has to organize anything ever, it's an enormous amount of work to make things happen and make it go seamlessly, and they do such a remarkable job with this thing every year, and it's it's a big, it's obviously a big service to the whole community. Hopefully you're enjoying that, benefiting from that, but I think it's just a remarkable thing. All right, so just to start out, ground rules. We have about an hour, I believe, and I have, intendedly more than an hour of stuff we could talk about, and you don't want me to, just do that for the whole period. So I hope that as we go through, we will hit things that you want to talk about or ask questions about. I hope you'll raise your hand, interrupt, and ask questions, because the intent is very much that. And I'll give you the roadmap of that coming up. But anyway, so what I'm going to be talking about today is going to be some sort of two main themes. One of them is more general, and it involves the question of how we can use in silico experiments or computational experiments to accomplish various things. And then I'm also going to talk about something called relational event models, which I don't think you've talked about too much. That may be something that's useful in and of itself for some of the work that you may be doing. And so what I'll do is I'm going to start out with kind of general background. I'll show some examples. I'll talk a bit about the experimental part. And it's going to be pretty high level, but just to kind of seed your head with some ideas. I'll show a couple of simple examples from the literature. And discuss some simple techniques that can be used and how we might use them. And then we'll talk a bit about REMs and what those are and how they work. And then we have a tutorial, which I will kind of walk through some of that. That's also something you have available to you, so you can go through it yourself at your leisure and whatnot. And again, there's a lot more there than we're going to have time for today, or in fact, we're intended to have time for today. It's more something you can do in self-study if you're interested in. Before we get into that, I do want to make and I mean, I realize the camera's rolling, it's a little dangerous, but I live dangerously, as you know. Just to follow up on some discussions that we've had earlier, I know we had a big discussion yesterday about the challenges of publication and of trying to take networks into audiences that perhaps aren't used to them, have an allergic reaction to them, right? The antibodies appear, they try to drag your paper off to the lysosome or something. But in any event, one thing that wasn't brought up, I should point out is that some of you most of you are relatively new to the game, think this is some kind of thing that happens to new people, but we, the seasoned, the veterans, we don't understand what it's like. It just doesn't happen to us. But let me reassure you that no, it didn't go away. I had an example happen to me. We had a paper, and it was in fact trying to take networks into a field that doesn't normally deal with networks, so very much what we're talking about. And we had a very angry reviewer that didn't like it. Moreover, argued our paper should be rejected because a previous paper from our group had not been cited sufficiently. And therefore, this paper should not be published either, which is remarkable. In fact, they went through our citations, apparently, on Google Scholar, and they discovered, which was a revelation to me and also very sad, that actually almost all the citations the stuff had gotten were from us, of our follow-on work. They also thought the work was extremely theoretical, which is why we had sent it to a theory journal. But anyway, so they were very, very upset and that our work was very bad and shouldn't be published. And that happened, 10 years ago, 15 years? No, that was like last week. Well, it wasn't last week, last few months. So indeed, guess what? You're never too old to have these exciting things. I get told I don't know anything about networks. I get told that, anyway, all sorts of things. So it happens. You're going to get these reviews, and that's life. Now, I will say this particular story has a happy ending. So we did go back to the editor and say, come on. That's a very weird reason to reject something because another paper that isn't this paper wasn't allegedly cited. I was like, well, is there a threshold number of citations that we have to have for previous work? Anyway, so anyway, I was like, well, if you think the paper is no good, then that's fine. I mean, I'm an editor too. If you don't think it has legs here, that's fine. Reject it. We'll move on. That's okay. But I want to hear you say it. And then they grumbled a lot and sent it back out for review again. And anyway, long story short, it did in fact get published, and well, we'll see whether more than just us cites the paper in the future. That we don't know. But anyway, so just bear in mind the travails that we all deal with in dealing with cantankerous folks who may be also confronting stuff that's different from what they usually see and challenging to process. Is something that you will have throughout your career. It's not going to go away. So sorry. But on the other hand, it happens to us too all the time. And you can persevere and get through it and in fact have a happy ending, it's fine. And if anything, you want to try to use it constructively. I mean, I think in this case, we did look at, okay, that review didn't have very many substantive comments, but it made it very clear that, we were really doing stuff they weren't familiar with, they didn't really understand, and we really did make a strong effort to try to, in revisions, make the papers as accessible as we could. It was a genuinely challenging paper. Even, my own opinion, it was a hard paper. We did our best to kind of make that something that audience could understand, and in the end, it did work out. So persevere. You will in the end be successful, but yeah, it's just going to happen. Try not to take it too personally. All right. So with that kind of general background, as I said, what I'm going to be talking about today is about doing in silico or computational experiments. Now, one of the things I should emphasize, at the very beginning of things is that, this is not a new idea. This is a very old idea. And in fact, when I started my career back in the 1990s, it was already an old idea back then, but certainly one that was extremely in fashion at the time. And a lot of us, in fact, did a lot of work with what are then and now called agent-based models, trying to probe the emergent effects of social mechanisms. So trying to understand a bunch of social agents, they're doing things, they follow certain kinds of rules. What does that do to the social structure and to dynamics that result? Okay, if you change the behavior of the individuals or the context the individuals are in, how does it change outcomes? And we probed that primarily by computational experiments. So we would change properties of the agent, change properties of the setting, simulate outcomes, and see how did that work out? What did it do? And so this is not a new idea, and yet if you look at the literature, I think you'd see people are starting to get back into this idea. So we might ask, first of all, it never completely went out, but why did it somewhat maybe go out of fashion, and then why is it back now? And I think to understand both of those things, it's useful to understand something else about that particular wave of research. And one of the things about it is that a lot of the work that was being done at that time was being done using models that were non-empirical. Okay, and what do I mean by non-empirical? I mean they involve fake people living in fake places doing fake things. Okay, you have little simulated people, they live on a grid. Often the grid was a torus, so they're living on a giant donut. And I mean, maybe you'd like to live on a giant donut, depending on the frosting and whatever, but most of us don't. I think it's safe to say live on a giant donut. The agents are very, very simple, and they would do things that were very abstract. They play some game, and then they would have an action that might be called cooperate or defect, or it might be called left or right, or who knows what it is. And they get weird payoffs that they don't live lives that look like mine, and not really anyone else's either. And although we were trying to use them to probe basic things about how do phenomena like cooperation, for instance, emerge, and what are the conditions that could do it, and I think we did learn something. It was a very frustrating endeavor at the same time because these models were not things that you could put in contact with data. Okay, they were not, and that meant they could not be falsified. They could not be wrong. Okay, a model that can't be wrong can't be right either, right? And that's pretty unsatisfying in the long run, right? So you can say, well, my little fake people in my fake world do these things when I poke them, and you're like, okay, great. But there's people out there in the world that is not so fake, and what does that tell us about them? We think it rhymes with the real world and tells us something, but what it tells you is a little slippery, right? And especially when you get down to brass tacks. So one of the early problems I worked on was simulating the emergence of these things called belief panics, where you get whole groups of people whole communities that could come to believe something that was demonstrably false. And there were a bunch of these that in the 80s and early 90s, for instance, where there were communities that became convinced there were groups of Satanists that were going to come kidnap their kids. And you had parents roaming the streets with baseball bats looking for satanic cults, and which is all fun and games, of course, unless somebody gets falsely accused of this sort of thing. And in fact, they were sort of linked to things that had very negative consequences for people. And of course, the question is, how can that happen? How can people come to believe these things? And we had models based on ethnographic work of what went on in these communities that could recapitulate a lot of things qualitatively that people thought they saw. But then, you got into the situation that, you could build lots of models that could qualitatively reproduce what people saw. And they were different, and they had different social mechanisms. Which one is right? We don't know. We don't have data to pry them apart. There's no easy way to do that. Okay, so if you want to do things like that, right, you start to become limited, right? You need to, at some point, you've got to get beyond having these kind of very stylized things. And that's very hard, right, because it was not obvious how you could put models like that in contact with data. And it meant we had to rethink the way we were modeling. And there were a lot of pieces of that. One is designing your models in the first place around kind of a simplified notion of agent that you could put data into, right? So not building your agent so it's dependent upon people living on a grid and so forth, doing two things that don't make any sense. Okay, so part of it is trying to ground it so you can have a world where you have agents that have attributes that look like, or at least can represent the attributes that we think people really have, that can do things that are more like what people really do, so that you could put data into it. And then, of course, the other piece is you then need statistical theory that allows you to take your model, which is still an abstraction, a simplification of reality, and then calibrate that model against some kind of observation. So you can actually say, I'm going to try to find the best estimate of, the best approximation in my simulated world of the world that we see in terms of something real. And that was a very difficult thing to do. And a whole lot of people, of whom I was one, but only one, spent 20 some odd years at least working on that problem. And that has borne fruit. So today, as you come onto the scene, right, you're inhabiting a world where people make you go to workshops and learn about these things called, ergoms and seoms and rems and all that stuff. And that stuff is the fruit of a lot of people trying to say, how do we build models that on the one hand are statistically well-founded? That is, I have some actual inferential theory that says that, under the right conditions, this model can actually emulate data not only in the case I see, but other things, that I have some ability to infer parameters, some ability to make extrapolative prediction, but then also to have these models reflect some things that we think are real about how the world works. Okay, because when I started, you could do one of two things, at least to a reasonable approximation. You could have a model that had mechanisms in it that you thought were in some rhyming way, like the real world, or you could have models that were statistical. So you could have statistical models with any line you wanted. Okay, you want a linear model? We got you covered. Okay, you want a t-test? We got that down. Okay, I'm of course exaggerating. There's a lot more than that, but to some approximation, like the models behind a lot of the statistical work were very simplistic and not very useful for social scientists who wanted to get into, emergence and mechanism. They weren't very helpful. On the other hand, right, we had these models that did capture that, but you couldn't calibrate them. And so bringing those two things together was an enormous amount of work. It continues to be. So we're not done, but we've made a lot of progress. And so we now have this sort of new generation of empirically calibrated models where we can take social networks, we can take social behavior, we can take the two of those things over time, we can put them together, we can actually calibrate these models against real data. And that's something that now gives us a very powerful tool, because to the extent that we have calibrated that model effectively, we can use that as an approximate, of course, proxy for a real system and do something useful with it. So that's one of the things I think that has motivated this comeback, is that we have been basically prepping for it for a couple of decades now. And now the stuff is getting mature enough that we can come back and start to go back to those old questions that we had before, but now see it with new eyes. That's one reason. Another reason is because, of course, we need models to do lots of stuff. And in a way, that has never gone away. But I think it's certainly a demand that we have today, right? We need models to do things like informed study design. So for instance, how many of you have ever done a power analysis? I better see some hands go up, okay? You ain't getting no NIH money without a power analysis. I had a grant. We also get, in addition to papers, we get grants rejected, just in case you're wondering. I had a grant rejected not that long ago, and reviewers didn't like lots of things they hated about this grant. But then there's this one comment, and they're like, nice power analysis. Knew that, yeah, they love that power analysis. Okay, if you've done power analysis, right, you may have felt like if you're not a statistician, it has a certain ritual character, perhaps. You may wonder about it. If you are a statistician, it has ritual character, and they can be taken a little bit ritualistically, but they serve a purpose, right? Why do we do the power analysis? Anyone tell me why we do power analysis? Other than you have to, or the reviewers reject your stuff? What's the point? Not an ex post facto, ex ante power analysis. It's someone, now you're afraid. It's like, oh God, he's going to do statistics. Yeah, I mean, trust is a strong word. That's an optimistic word you use. But yeah, right. I mean, why do we do this, right? In theory, it's supposed to be something that protects us from a certain kind of error, right? We might go out in the field. We take our very precious resources that were very hard won. We recruit subjects who are taking as we talked about last time, they're taking their time. Maybe they're putting themselves at risk. They're creating social obligations that was talked about to participate in your study. And you don't want to go out there and burn all those resources only to discover, actually, we didn't have enough data to tell if the intervention we were doing worked, right? Or to tell whether the difference we're testing is even there. Sorry, everybody, that was a false alarm. That's no good, right? It doesn't bode well for you being able to go in that community in the future, right? Or do other things, right? We need to get answers that we have some confidence, which is the right word if we're doing a frequentist thing, right? Have some kind of meaning. So if we don't see an effect, for instance, we want to think that means that probably not much is going on, not that, sorry, I didn't have a big enough N. And power analysis is a very limited tool, but it is in a way of kind of, if you like, simulating a hypothetical result ex ante and saying, if this effect were there, how likely would I be able to see it? Right, if something was actually present. And we want to confirm that if there were an effect, at least of a certain size that we think is realistic, we would have the data we would need to be able to tell. And so we make people go through that exercise, because if you don't, right, you run the risk of wasting everybody's time and resources, which is not so good, right? And that's among other problems with it. So that's one of the reasons we do that, and it is actually kind of important. No one likes it because it's a pain, and it always tells you things you don't want to know, like your N is not big enough, and they will not give you enough budget to get the end you want, okay? But it's protective, right? And there is a reason for it, right? So that's a very simple example, but of course there are other things that we may want to do in that vein as well that are more complex. So for instance, there was a lot of talk yesterday about all the complex things that can go on in interventions and how they can go wrong. And of course, if we're intervening in a social system, things might be complicated. People might influence each other, for instance. And that ideally ought to be part of our thinking. We think about what might happen. Of course, something like a t-test is not going to protect you from that. But models may give us a way of knowing what might happen, hypothetically, if we went into a system that did something. Okay, and that can allow us to check ex ante, am I likely, for instance, to have an intervention that's going to be big enough to be effective? Am I targeting people in a reasonable way? And of course, it's not going to tell us everything because we're basing it on a model, which is certainly imperfect, but it could give us some kind of an attempt at an answer that could help guide us. And of course, some of you, if any of you do any biomedical stuff, any of you ever been involved with or aware how pharmaceuticals work, if you think about drug design, drug discovery, right, there's a very long chain, right? We don't just get some stuff out of a sea slug. It's always a sea slug. An organic chemist, it's always, you sit on a cancer research panel or whatever, they're always like, well, we have this drug, we have this great anti-cancer compound we want to get. Okay, why do you think this is a good compound? It came from a sea slug. I'm like, okay, but why is this good? Sea slug. They really do this, I'm telling you, you see on the panel. Okay, not very convincing perhaps, right? But the problem is, okay, you get this lovely compound from the sea slug, and then what do? You test it, in vitro, and you see, does it do something in the test tube that seems reasonable? And if not, you throw it away, you get a new sea slug. If it does, right, what do? You take it to cell lines, right? You test things against cell lines. So if I have actual cells, right? Now why should I have to do that? I had a great molecule. Why do I need to test against cells? Because cells don't work like little stuff in a test tube, okay? Even though they're very simple, right? You might have this lovely drug that you made, but it won't go into a cell. Or it goes into the cell, and then the first thing that happens is the cellular police grab it and haul it off to the lysosome to be broken down, okay? And, oh, sorry about your drug, didn't work, okay? So you have to test that, and then of course, even that is not as good as testing a real animal, and of course we have many, many stages up until we get to humans. A part of that is safety, but also a lot of it is efficacy, because there are many, many reasons why things might not work, even things that are really good ideas. So the person who maybe originally had that, maybe they did something more clever than dropping it out of a sea slug, they may have had a really good idea for why that molecule was going to make a great drug. And you see a lot of that with drug design, especially these days, people trying to do very, very clever things. But most things don't work out. And so before you invest all of that time, effort, and risk in putting things into people, we have many stages where you test the idea first. And we try to do that with social interventions as well, but we often, I think, don't have maybe as many steps as we might in that process. And one of the things that can be helpful with in silico experiments is that they can give us another step into thinking about what would a successful intervention need to look like, how many people would I need to hit, how would it have to work, how big an effect size should I expect, and so forth, in a more realistic setting before we have to go out and propose something and intervene with real people. And the more stages, on the one hand, you might think this is lame. You're saying I have to have more steps to go through before I can get out there and deal with people. Well, in some sense, yes, but in the long run, the idea is this is good, right? Because it can give us more ways to probe our great idea before we actually have to go out there. Because there's lots of great ideas that just don't work for lots of reasons that are hard to see ex ante. Not all of them will we be able to see with something like that, but maybe a few of them. And if it prevents us from screwing up, that's a good thing. So, that's one reason. Policy, likewise, right? You want to know what might happen if you implement something. Are there side effects? You have some system, you have some intervention in a classroom you're going to do to try to, say, shut down some behavior that you don't like. Is it going to, however, also result in people, say, becoming socially isolated? Oops, Are there side effects? We never probe for side effects with social interventions, right? But of course there could be. These are things that we might want to look at as well, right? So there's need for it, and then as you've alluded to it, right? There are limits to using models to understand complex systems the way that we often do. And so another thing that I think is pushing this mode of thinking about things, and I think some of the previous days have also alluded to this, is that I think if you look at how people often use models, they're often used in a very limited way. So you'll see a lot of work in literature, and including plenty of mine, where people break themselves to make some fancy model, they fit it to data, and then what do? They read off the coefficients, and they look at the significance of the coefficients. They say, I found an effect for gender on such and such. They declare victory, and they go home. And you're like, wait a minute, what happened to that model? Okay, you spent like 2 months making that model, and you used it as a fancy t-test. Okay, that's not really telling you much, right? How is that effect actually playing out, right? And if you're talking about a complex system like linear regression, okay, things aren't linear. You want to know what is the real effect of this variable, and to get at the sense of what the real effect is, right? We often need to do something that's more like an experiment, and we can't perhaps do the real experiment, but we can do the experiment in silico. So that's another reason. So there's a lot of reasons to do all this stuff, and hopefully, by the end, you'll have more of a sense of it. All right, so let's get into some things. So there's many, many, many ways to do computational experiments. Lots of them, and you will not see them today on all their glory, but let me give you a little bit of a recipe that I think is generally useful for a lot of things. I will use notation because they would take away my mathematical scientist license if I didn't, but it is really there to make life clearer, actually. So let's talk about a basic recipe. So here's a broadly useful procedure for thinking about many kinds of in silico experiments, just kind of informally summarized. Right, so I'm going to start with some kind of data and I'm going to represent that by Z here. That represents my observations. Maybe you went into a classroom and you have who talked to whom over some period of time. Maybe you have gone and done an RDS study and you have information about drug injectors in some community, whatever it may be. You have your observations. And we also have some model that we have proposed to account for, recapitulate those observations. We'll call that M. And of course that model, it depends upon some theta, some set of unknowns or parameters, and of course some observable covariance. And so of course what we're going to do first is we're going to take our model, we're going to fit it to the data, we're going to calibrate it so that as much as possible, right, it reflects what we think is going on. Having done that, we're now going to choose some statistic of substantive interest, some outcome that we're interested in. Perhaps I'm interested in a classroom setting or in a school setting, how many people are smoking or drinking or having fun in some other way. And so let's let F be that statistic. It's going to be some property we care about. And so then what are we going to do? The first thing we're going to do actually is before we do any other fancy experiment, we're going to simulate draws from our model. So we're going to take our model, we're going to run it forward. We're going to look at alternative outcomes the model might have. So if we're looking at, say, smoking in the school, we're going to simulate the behavior of people in the school. From our calibrated model, we're going to see how much smoking there is. So we're going to simulate it a bunch of times, we're going to calculate our statistic, and we're going to compare F of Z, which is the actual observed statistic, to what the model is producing to verify adequacy. Adequacy checking is very important, right? We want to make sure that the model is producing credibly something that looks like what we saw. Otherwise, the model's probably not great for that purpose. By the way, models are models. Models aren't real. I was at once I gave a talk and someone came up, I had a poster, someone came to a poster, I had a model. This person said, well, how do you know this is true? And I was like, oh, I can help you with that, it's false. Easy. They're all wrong, okay? As the saying goes, right, famously, all models are wrong, some are useful. The question is it adequate? Okay, adequacy means, is it reproducing what you care about well enough for your purposes, right? Some things it's not going to do, some things it is. So you need to make sure it's useful for the thing you care about. If you're interested in reproducing drinking behavior, your model is not reproducing drinking behavior, probably not so useful for what you want to do. So we verify model adequacy, and then having done that, now all we want to do is consider a new set of alternative conditions where we're going to examine the model. And those might be things where we might change, we'll see examples. We might change the parameters of the model, so we might change the social forces that govern how the system works. We might change the covariance, we might change the setting in some way. What if the mix of students was different in the school? How might it affect things? We're going to define a set of conditions by changing those things. For each condition, we're going to draw a new sample. So again, we'll simulate hypothetical outcomes. So we're going to have hypothetical schools with these hypothetical different kids in them. We're going to look at outcomes in those hypothetical schools. And then, of course, what do? We now analyze the cross-sample variation across our conditions to look at what the impact of theta, that is our forces or parameters are, and the conditions set by the covariates are on F with respect to M. And there's a million ways to use that basic recipe, right? It's very simple, right? There's actually nothing very fancy. We're doing just what you would do, right, in any kind of sort of experimental design. But the key thing, right, is that we're going to do this in model land. In model land, we can change the way things work. And we want to know, how does the thing we care about altered by those changes? Now, of course, it's a very general recipe. You can use a lot of ways. There are many kinds of things you can do. Here are a few examples of common types of experiments. And again, none of them are novel. You'll also see them go by different names. I'm going to use some nomenclature here, some of which is sort of borrowed from biomedical world. One, because I think they actually have a fairly nice way of thinking about how you do experiments with complex systems, because they have to deal with complex systems. If you study frogs are pretty complicated. And you want to know what happens if you what's going on in a frog, say optical system, you have to think of what happens if I intervene on the frog, right? We have to have a way of thinking about that. And so, frog is complex, just like a school is complex, and they've developed a whole lot of nice ways of thinking about it. So I'm going to use some terminology related to that. So one kind of thing we can do is what's called knockout experiment. The idea of a knockout experiment at a high level, so this is just bumper sticker level, is we're going to take some mechanism that's active in our model, and we're going to turn it off. Just like you might, so this is borrowed again from a biomedical context, there might be some mechanism in that frog. Say you have an enzyme that makes an opsin, it's in the frog's eyes, help the frog see, you think, but you don't know what that really does. If you didn't know, you might say, what's the effect of that? We're going to knock it out. So we'll turn it off. Maybe you CRISPR it out, maybe you put some interfering RNA in it, whatever it is, you knock it out, you turn it off, and you see what happens to that poor frog, right? And you compare the frog with and without this mechanism. So say in the school, I'll show you an example in a minute, we could take something like, say, social influence, peer influence, and you might say, what happens if we turn peer influence off? Okay, now note, I'm not saying that I can go into a real school and turn off peer influence, right? If I do that, I would need the model, right? But in a model, I can. I can go in and switch that thing right off. And then we can say, what's the effect? What does it do if we turn it off? Okay, that tells us something what the mechanism is doing, right, by comparison. We can also, of course, we can knock things out, we can also knock them in. We can take a mechanism that wasn't there and we can add it. So we can add something that wasn't happening in our calibrated model. We can see if something does. Let's say, for instance, that you're looking at smoking behavior. Let's say that actually empirically you saw that there was no avoidance of smokers by non-smokers. Now, in fact, in practice often do see that, but let's say you didn't. You could say, well, what if we had a norm that emerged for people that want to hang out with smokers? What would it do? So we might add that to the model and then say, okay, what does it do? So that's called knock-in. We can knock things in and out. We can knock them up and down. We can just take all our prepositions. We can just use them. Okay, so that's just where we take an effect. We can amplify or attenuate it. Sorry, what?
Do not knock up your model.
Yeah, that's it. Well, yeah, there are things that are yeah, we don't talk about in these types of things. So that's left to your own devices. So we can take an effect and we can amplify it or attenuate it. And then, of course, we can do other things. So all of these involve changing basically the parameters of the model, okay, the things that govern the forces, the mechanism of the model. We can also change our context, right, or our covariates, right? So we can, for instance, change individual settings or feature settings from the calibrated scenario. So again, in our school, perhaps we might change the number of students in the school, or we might change the characteristics of those students, the demographics of those students. Okay, the grade distribution. We could change things like that and say, does it matter, for instance? And why would we want to do that? Well, there's a lot of reasons. One might be robustness. I see something going on in a certain school. I might say, but how might that play out in a larger or a smaller school or a school with different demographic distribution? Okay, I can't know for sure, but I can at least sort of say, well, if things worked otherwise the same way and we change that characteristic, what effect would we expect it to have? We can change the characteristics and see what does it seem to do. And that gives us some insight into what might happen. And then we can do other things. Here's another example of something that's a little more complex, but interesting. If we have dynamics, so if we're simulating not just a static situation, but something emerging over time, we can do things like interrupted sequence experiments. So we can take a dynamic process, we can intervene in a particular point in time, and then change something, and see what that does to the continuation of the sequence. So for instance, to take an example that we studied, not a health example. Well, it was related to people's health, but not in the same way. Looking at communication, the World Trade Center disaster, which actually we'll see an example of that later. Some of these models were actually invented to look at that data. We looked at communication patterns, and then actually did interruptions, so we could actually say, okay, what happened if a bunch of people in that event were incapacitated partway through? Which is, of course, something that happens in disasters, right? So if a bunch of for instance, your coordinators who are organizing everyone, what if all of a sudden something bad happens to them? What happens to the system? So we could simulate behavior, we can interrupt partway through, we suddenly incapacitate them so they can no longer respond to anybody. And then we see what happens to the rest of the system. How do the other agents, can they figure out that these people are now gone? Can they reorganize? Okay, what happens to the network when we do that? And so that's something we might be interested in. In a lot of intervention settings, you might be interested in interruptions, right? If someone is on some pathway to addiction, what happens if you do an interruption? What will happen? And we're comparing then the control timelines, right, where we don't do anything to the ones where we interrupt. So again, lots and lots of things we can do. This is just whetting your appetite. So let me show you a couple of examples. There are many more, but here are some from a couple of papers. This one, I apologize for the lousy figures. We should have done a better job with that, but okay, we didn't. Anyway, so this is Lacon also. This is stuff with Cynthia Lacon, John Hipp, Cheng Wang. What this is looking at is it's looking at smoking behavior in some of the ad health schools is simulated using a stochastic actor-oriented model, so which I think you've heard about. So your models where people have friendship ties, they also smoke, and they influence each other. Lots of things are going on in the model, but what we were interested in at the time, this is of course many years ago, is this simple question of what happens to behavior if you modify two mechanisms that are thought to be important. And one is selection, partner selection. To what extent am I prone to hang out with people who have similar smoking behavior to my own? And then the other is social influence. To what extent am I likely to emulate my peers in their smoking behavior? And so what we've got here is different smoking levels as a function of the relative value of the parameter. So 1 here, which is right here, is observed. So this is what we calibrated as model 2. We can take this thing to the left and shut it off or turn it down. So we take it all the way to 0. 0 means it's just gone. We knocked it out. We can also amplify it. So we say, what if it was stronger than real life? What would we expect to see? And there's a bunch of curves here, but these are just to look at the top line, which has to do with people who don't smoke at all. And so if we looked at what we saw, this is 2 different schools here. What did we see? Well, if we took selection, so that's again the tendency, to what extent do I want to hang out with people who are similar to me in smoking? We saw not an enormous effect of selection. One school doesn't do much of anything. And another school, actually, if you turn it off, there's a little bit of a decline in non-smokers. So you see a little bit of smoking. So to the extent doing anything, like selection may be kind of inhibiting smoking a bit, sequestering smokers by themselves, but it isn't doing a whole lot. If we look at influence, it's a much bigger effect. But one thing that was interesting at the time, and some people still, I think, is kind of interesting, is that now there's a whole story, right, that people like, that the effect of social influence is to make good, clean, happy young people turn to darkness. And, they smoke and they drink and they dance and they listen to that hip hop stuff that who knows what they'll do next. They get long hair. Scary stuff, right? But actually, right, if we go back to our core social theory, we know that the main effect of influence is to suppress deviance. Actually, right? Because if you're being influenced by people like you, or people not like people around you rather, to be like them, okay, then we know something, and that is that the people around you, who you're tied to, on average, are more normal than you are. That's a regression effect, regression to the mean, right? So on average, right, your neighbors are more boring, right? Okay, more normal. So if you're influenced toward your neighbors, on average, you're going to be more influenced toward the population average, right? That's what we would expect to see. And so in an environment, now this is key, asterisk, right, in which smoking is relatively rare, which is true here, right, then what should happen is that actually influence should be suppressive of smoking. And that's exactly what we see. So if we turn off influence, what happens is actually the non-smokers go down, smokers go up. So actually more people smoke. And if we turn up influence, we make social influence stronger, smoking goes down. We see more people who are non-smokers. So it's actually the opposite, right, of the effect that people might think. What's going on is that smoking, in that sense, we would interpret as saying this is a protective effect versus, influence is a protective effect versus smoking in this environment, right? Which is not what you might think. Now, if you just read off a coefficient of the model, that wouldn't be obvious. What you would find from the model is it says that people have social influence or smoking, right? So if you believed in the seduction to evil kind of, argument, you'd say, well, see, this is exactly what I've been telling you the whole time, right? You're around smokers, you're going to become a smoker. But that's not the whole story in a complex system, because everyone's influencing everyone else. So not only are the smokers influencing non-smokers, non-smokers are influencing smokers. You have a lot of people who actually might be inclined to light up, give it a try, right? Except that they're surrounded by non-smokers, right? And they'll be the only one doing it. Right? And so in fact, what we see is sort of the opposite. So this is a long time ago, a very simple model, and other people, David Schaefer, others have also probed things like this. But it shows us a really simple example of why actually using a calibrated model and doing an experiment provides an intuition that's very different from what you might have if you just looked at the model alone. Now, that's an example, of course, of a situation where we have a knockout experiment. We can take this to 0. We can knock the effect down. We can knock it up. We had a lot of different things going on in this one plot. But it gives you the idea. We can do other things too. Multiple knockouts. This is a more complicated one. I would go into great depth about it, but just to sort of show you can do it, this is the same crew This is a 3-behavior case looking at smoking, drinking, and marijuana, so a whole lot of partying going on. Here, we're just looking at different knockouts. So we had different combinations of effects that we could take out and see what was going on. And this is sort of the multiple relationships in the model. If you have two people, basically, of course, you could have all these complicated things where people could influence each other directly, but of course then their own behaviors might influence their other behaviors. And so how does this wind up working out? It's very hard to tell from the coefficients because they don't tell you how the whole system works. But if we take a knockout, we can get some insights, right? And so one of the things is to sort of say how it wound up working. So up here we have these are non-smokers, heavy drinkers, and non-marijuana users at the top, just so you can see what those are. You know, we find on the one hand, if we knock out social influence, we actually see that it actually changes substance use in different directions, as we would say. Sorry for the, well, there. What it always is wind up doing is it's having the same substantive effect. It's increasing the use in all of these cases. So it's compatible with what we saw in the previous case. So we actually have more total use. But we can also get other things. So for instance, we found there was a pathway from marijuana use to drinking and smoking. And it actually turns out that pathway, if we knock that out, it suppresses drinking but not smoking. So people talk about the pathway of the idea that their hard drugs are enabled by softer drugs, but we actually don't find that. But the other way was found. So it's not that people weren't going to use marijuana because they were smoking or drinking, but they might drink more from marijuana. So in fact, you can get some of these effects. So these are again things that when you knock stuff out, you can start to probe. Here's another kind of very different example. So how about targeting? Let's say you want to go out and you do an intervention on individuals, but you know they influence each other. So you might think, well, if I intervene on those individuals, they'll affect others in the environment, right? And in fact, we might hope to do that. That's the whole point of network interventions. Tom, of course, yesterday was here. Tom was one of the big proponents of network interventions. But there's a question of, okay, who do we target with that intervention? And so here's a result from another study by the same kind of crew. Again, using simulated experiment, same environment, also looking at health as an example. This is looking at drinking, and the basic idea is like, imagine that you have an intervention where you go and you just grab 20% of heavy drinkers, and you were able to stop them from doing that. Now, can you really do that in the real world? That's a whole other question. But what in our simulated world we can ask, what's the net effect of that on the number of non-drinkers in the school? And so, if you just, so this is the baseline you get if you do nothing. If you just do and intervene people at random, you wind up with indeed slightly more people who don't drink. So that does have an effect, as you might imagine. But if you look at these other effects, you can see that there is actual variation, right, in how big the effect size is depending on how you target people. So what we did is we looked at different things, like do you target people by their in degree, by their closeness, by betweenness, by different network characteristics. And actually, if you target people based on their eigenvector centrality or their in degree, you get rather larger effects. And this is something that we've seen in other cases as well. So it matters how you pick targets for things. And of course, you can't know for sure how things will work out, but using a model can give you some indication of what might happen. So if you only can afford a small number of people, you want to maximize potential effect size, especially from your indirect effects of the intervention, right? It may pay to do some simulation work and actually say, okay, which targets are likely to be most effective? And this is something we can try to probe. And there's no guarantee that it's going to be right. Of course, it's a model. But if the alternatives are, drawing a map from your imagination, with apologies to the great Professor Elemental, or actually using a model that's empirically calibrated, you've got a better chance of getting it right with something that's actually guided by data. So that's hopefully your appetite for the idea. The time I have left, I'm going to say a little about REMS. And we'll say a little about in silico experiments with REMS. I think just given time, we probably won't get too much to actually doing the health examples. But all of the examples that are walk through doing these kinds of things that we've talked about with REMS, there's a lovely tutorial for this. You can find it on the StatNet website, and we'll also put a version up on your thing here. And you can walk through this yourself and run on your own computer, and then modify the scripts and do your own experiments to your heart's content. You can see how it all works. But what I want to do with the time we have is talk a bit about REMs and how they work first, as that may be useful in and of itself, but also to motivate some of those other experiments. All right. So what's the deal with REMs? So the story of REMs goes back to basics of what we do in network analysis, right? So I'm a networker. I'm interested in relationships and the patterns of relationships. And in the network paradigm, right, what we typically do is we focus on relationships that are temporally extensive, and that may not be something you ever really thought about, but it's true, right? We study, say, friendships. People go seek advice from each other. These are relationships that have some existence in time, right? They're not fleeting, at least we hope not, right? Some friendship has some beginning, it has some end, and in between there better be some period of time. It's non-zero, right? In fact, usually it's quite long. People's ties turn over, but they turn over relatively slowly compared to what goes on inside the relationships. And that's what allows us to talk about things like, say, betweenness, right? In order to have something like that be meaningful, we have to have the idea of a chain of contacts, right, within the network, right? So we have to have ties that are co-present. And in fact, most of what we do in network analysis, it fundamentally comes down to the fact that relationships are coterminous. This one is present while I have that one, and so this one can affect that one and vice versa. And that's very powerful. We write lots of papers about it. But it's not always ideal, right? Because sometimes what we're interested in is the social action that lies beneath the relationship. So we're not just interested in the fact that there's a relationship between two individuals, but in the back and forth interactions that occur inside that relationship. And in that context, we may need a different paradigm. And so to just sort of illustrate the one that actually sort of started this, just to give you a bit of the story of how does the science actually happen, it's always messier than it sounds. So this is the case, this is actual data. This is data from the World Trade Center disaster. And so what we're looking at are radio calls between responders to that disaster. In this case, this is, so these are individuals that are carrying a fixed frequency radio, or they're wearing fixed frequency radios, aka walkie-talkies. They only have one channel they can talk to. That's for their organization, so everyone in the organization can talk to everyone else, but not outside. This is the Command Post Dispatch channel at Newark Airport. They're responding to the event. And so, of course, on 9/11/2001, we had a terrorist attack in the United States. A plane hits a building, and it's going to be a bad day for a lot of people. And of those who responded, right, in units in the WTC and other units, all of a sudden, they had to do something about that. And in the case of the airport, all of a sudden they had to shut down the airport because all air travel in the United States was closed, all the airports were shut, and they had to clear out the facility and deal with people, and making sure that there were no attackers or other things going on in that event. And so this is the individuals communicating with each other during that process. And so if we were to look at that as a network in a conventional way, we might do something like this. So each individual here, each node is a person. There's an arrow from I to J. If I sends communication to J during the period, I've sort of scaled them by how much communication. And we first got the data, was a long story there I won't go into, but we started analyzing it like this, being good networkers, we learned a lot actually by doing that. It's a good thing to start doing. But lots of questions came up about, well, what's going on in terms of the social process that generates that network? Okay? Because at the end of the day, that's not really what's kind of going on, right? What's going on in the data is more like this. Okay? So these are the actual calls. So this is an animation of the actual process of people calling each other back and forth. So under the hood, this is what we have, right? It's not ongoing relationships, right? They are exchanges, right? And each exchange is a kind of fleeting event. Of course, there'd been a lot of work, and particularly work by Jim Moody had been doing about if you have data of this kind, how should you kind of try to segment it in time to not lose too much information? And it's really brilliant work. As we were thinking about it, we're like, well, we could do that, but what would be better is to not segment it and not accumulate it at all. What if we were to try to think about it in its original terms, okay, which is this set of actions? How could we do that? And that required a different kind of paradigm, which is what led to the idea of the relational event. So what's a relational event? Okay, basically it's a discrete event where one or more entities emits a behavior, one or more emits environment. That's a fancy way to say it. It's basically something that we can depict as some kind of action or interaction involving individuals. And so we can represent them, just as you think about representing an edge and network, right, by I-J pair. We can think of this like a tuple that's got, there's a sender or receiver. In some cases, there may be attributes of the kind of interaction it is, but the key thing is it's got some moment of time. And the big thing that makes a relational event distinct is that we can think of it as happening at a moment in time. Now, of course, in the real world, nothing is truly instantaneous, but when we're in the regime of relational events, the duration of the interaction is small compared to the overall dynamic, so we can approximate them as being sort of instantaneous. And that creates a very different world, because in the world of networks, right, we have relationships that are going on simultaneously, but in the world of fleeting events, right, they're well ordered. So we're no longer interested in things like paths in a simple sense. We're instead interested in sequences, okay, sequences of actions. Yeah?
Sorry, maybe jumping the gun here, but
Yeah.
for the action type, do you also have some type of weighting mechanism for the possible action if it is some type of quantitative value?
Could be, yes. There's a lot of things you can do with it.
Probably jumping the gun here,
Yeah, there's a lot of things you can do with that. But yeah, I mean, the simplest version, we just think of actions happen when there's one kind, but you can have all sorts of complexities with it. So again, I already said what the deal with the case was. It's what motivated us originally, right? We were interested in the mechanisms that led to the emergent structure that we had. And as you go through the tutorial, you'll see probing this a bit of why did we wind up with some individuals who wound up being these hubs who held the whole network together, and why not others? And we actually found just doing traditional network analysis that the people who were, and these are two students of mine who did a lot of work on this, we found that a lot of the people occupying these positions did not seem, in fact, to be people who had special roles, but in fact, they seem to be emergent. So some people wound up being in these key positions holding the network together, and the question is sort of how does that happen? And to do that, again, we needed this kind of modeling approach. Now, again, how do we think about this? So we've got relational events. How do we think about analyzing them? We borrowed basically ideas from hazard analysis, event history analysis, depends on what field you're from, what you like to call it. But we think about all the actions from our time 0 up to some observation time, form an event history, it's just a set of all actions that are whose time are in a certain window. And so then the possible actions at any given time, right, are going to be some subset of the possible senders by the possible receivers by the things they might do. And so then what we do is we model that event history by treating the actions as statistical events in continuous time. We're going to put hazards on those events, so a propensity of events to occur, given the current history. That in turn shapes what occurs. Then when an event happens, that might change the propensities, right? People may react to what's going on, which of course sets the stage for the next event, right? And so we can do that with things like the WDC. We had other things. This is a nice example. This is from Dan McFarland. His data set. Here's a classroom, and you can see there we have individuals sending information. This is a teacher. We also have group events. The teacher addresses the whole class. We have things like that, and so we want to be able to handle this. And so how do we do it? Well, of course, we do it statistically, as we said. So how can we actually define models on these types of things? And it turns out we can take very natural ideas from the kind of event history, hazard modeling, survival analysis, pick your favorite literature. The basic idea, just to give it at a high level, is that we're going to think about our propensities of actions to occur by a hazard function, which we usually use this sort of log linear form. So we take the hazard of a specific event, given the history and the parameters to happen, as the log hazard as being a linear function of a set of statistics that are fairly general functions of who would do the action, who would be receiving the action, what kind of action it is, what's happened up till now, and covariance. And then this just says if something's impossible, it doesn't happen at all. Of course, there's an overall pacing term that says how fast things happen. And so it turns out if you make some simplifying assumptions, we could actually write down the likelihood for this. So the likelihood looks like that. And I don't want to belabor things, but for people who've seen kind of hazard modeling, you'll look at it and go, oh, actually, I recognize that there's nothing really fancy going on. For those who haven't, and you're like, there's a lot of notation. What the hell is going on? Here's what it basically says. It says the probability density of an event history, so the likelihood of the event history up till now can be thought of as a product of things where we go to the first event and we say nothing happens until the first event happens. That's the chance that nothing happens until the event occurs. Then something happens, and this is the chance that the thing that happened, and then we wait for the next event. That's the chance of nothing happening till the next event. Then the next event is the one that it was, and so forth and so on, until we get to the last event, and then this says nothing else happened until we stopped watching. And so that's what all of that is saying. So key thing is we can write that down, and then of course we can calculate. And if you're familiar with ergoms, and there's been some discussion of that, these things can be devilishly hard to calculate in practice. One nice thing about REMS is this is a relatively easy thing to calculate. So it's a lot, not always cheap, but it's much, much cheaper than it's often the case for things like ergoms and the like. So then how can we do inference? In practice, we're going to observe data on the event history. We parameterize our model by specifying the possible mechanisms that may be driving behavior, and that's done by choosing our statistics just as they are in a SEOM or an ergom. And then we can infer theta by your favorite likelihood-based method. You can use kind of any approach you like. You can do maximum likelihood estimation. It's fairly straightforward. If you're a good person, of course, you'll do this in a Bayesian way. And we have lots of ways of doing that as well. There are some computational challenges when the number of possible events is big, but they're relatively easy. So in the grand scheme of things, it's actually not so hard compared to a lot of other things, making these quite nice to work with. So I'm near the end of time, but what I want to do in this just quick couple of minutes is just sort of, I'll just point you again to this tutorial and give you a sense of what's in it, and then you can, in your as homework, right, go through and play around with some of these things so you can sort of see them for yourself. So this is what the sort of tutorial looks like that's on our site. This is actually very typical, by the way, of the StatNet tutorial. So we have this as an open tutorial. Anyone can use it. It's set up so you can load up the software and use it yourself. This uses something called the relevant package, so relational event. If you use it, you'll stop being able to spell the word relevant correctly, ever. And it does it, but it builds on the rest of the StatNet toolchain, which a whole lot of people have had a hand in developing. But you can see that what we'll do in that is it'll walk you through how to load stuff. It'll, there's a little more review of what I already talked about in silico experiments. And then it'll walk through how to fit the models. So you'll see how to actually fit that yourself. And evaluate the models. So we'll show how we see if it's working or not. The WC model, class group data model also in there. And then it's going to walk through a couple of different kinds of experiments. So we'll talk about how to do knockout experiments. So it'll walk you through doing that. One of the things you look at is, what if we take a social mechanism like the tendency to respond to somebody else when they call you, and how does that affect something like who becomes a coordinator in the WTC? And in fact, you'll see, it turns out to make a big difference on who winds up becoming central in those networks. So a little tiny social norm involving how communication works turns out to actually drive the social macro structure of the network. Talk about how to knock in various mechanisms. So what happens if you have gender effects on tendency to initiate communication in the classroom? How does that affect classroom communication? So you'll see how to look at that. How to change, what happens if you change roles in the classroom? So what if we create anarchy in the classroom and we actually get rid of the teachers? What does that do? What if we change the number of people with particular roles? And why do we do something? What if we have some intervention? Like, why do we take a teacher out of the classroom partway through? What will that do to the social dynamics? So all of these are different examples that you see if you walk through the tutorial, and it will show you how to do those types of things. Now, of course, given you're here for health, you're probably not interested in those specific questions, although you might. But the key is these are all examples of things that you can do with your own systems to probe things that you might be interested in. What if I change who's in a setting? What if I change people's attributes? What if I change social mechanisms? And you can see how to do that. And then finally, at the end, the tutorial talks about, so this you might want to skip to, is sort of what if I want to do a simulation from a relational event model de novo? So what if I want to just postulate a model and then actually get event sequences? And I want to experiment with what happens if I create different social mechanisms and play them out. So there's a whole way we can do that in StatNet. And so this just walks you through how can you do it, what if you want to use time varying covariates, all that kind of good stuff. So the tutorial will actually let you go do it. You can play with it. You can try. I encourage you to try other things out. So it will walk you through particular kinds of changes. But you should try messing around with other stuff, right? And see what it does. And so take the recipes in there and modify them. So if I am right about time, I think we're at the normative time. But I'm happy if we want to end up, if people have like last questions before we break, I'm happy to field any. Last question. Okay.
Have you ever used this to like approximate like how social dynamics and intervention will work and like follow up? What do you really see like how well? Because I know you said it's not the truth, like I love that the same, but yeah.
Follow up? Like I'd have to collect data.
Okay.
Do I look like a data collector? That's hard. I only do easy things.
Like if you were like on a team.
No. It's a very good question. Your question is very good. I'm making fun of myself. We haven't had the chance to do that ourselves, but this is something that I mean, we've been trying to figure out how can you get it to work at all. But this is certainly the kind of thing that I hope people will go do. And then I think, among other things, that's going to create a lot of insights into where the failures of the models are. Not just the how well do things work in other respects, how well do your interventions work, but how good are the models at actually when you have to extrapolate outside of the terrain, how do they do? But I haven't had a chance to do that yet. I'm hoping that will happen. Part of the answer is we have to get the hooks, you guys, right, to actually go out and do the hard work, right? I mean, we do the easy stuff, right, to actually go and implement that. But this is something that I think is right for people to do. Like what actual trials of model guided interventions. I think it's a great question of exactly where do the things work, where do they not? Because what we're going to find is it's always going to be a mixed bag. And how can we make models that are more kind of stable under that type of use case, right? Because what we've been doing so far primarily is we get observational data. We only get one stab at reality, we don't know how well they work outside of that. And that's something that the only way to find out is to get more data. And that means we need people to go do it. I don't know, Jim, if you know of examples of doing that right now.
No, I know of no one who's doing that right now. I think it's super right. And I think this really reflects back to the conversation we had on Tuesday that you were unfortunately missed.
Yeah.
I'd love to hear your reaction to, which was that when Scott Duxbury was talking about his micro-macro model, he was really, really cautious about how changing a micro-parameter would apply to change to a future change to a macro parameter, but you couldn't possibly infer that out to the world that set. And you're taking, it seems to me, a much more sort of hypothesis sort of set. This is generating hypotheses for the world out there.
Yeah.
But I'm just curious how you describe a result like this because I think as a reader we say, this is what the intervention is going to do in the model, and the scientist told me it's what it's going to do. But the scientist says, you can't learn anything, and I want to find something in the middle that we can say from that.
That's right, and I mean we have so outside of the world of this, where this stuff is just being able to do it at all is just maturing now, really. And then it's a matter of getting people to have enough trust in it to say, okay, I'm going to actually roll some dice and try it. In other fields, though, we do have a history of people trying to do this, and the results are mixed. Again, going back to things like drug design, you can find some things work quite well in terms of computational models. That nowadays, people use a lot of that stuff works very badly. And so I think that's an area that's useful, at least to me, that I look at as sort of inspiration of what we might expect. And so for instance, if you look at drug repurposing studies, there's a huge amount of work trying to use various computational methods, nowadays AI, we'll do other things to try to take drugs that are already FDA approved and then see, can you use them for something else? And to my knowledge, I think it's still true that there are no successes in this, despite years of effort. And I mean, I played with it myself. During COVID, we did some stuff and trying to find inhibitors that way. Yeah, it's easy to get stuff that looks good in a model, and for many reasons it just doesn't work in practice. So some things fail. On the other hand, people use models to guide what's called rational design all the time, and often with very good results. And in terms of getting qualitative insights about why certain things happen, The models are often very good, and you can use them as very good proxies for like, are two things going to stick together, or how is this faster than that? There's a lot of things that work. So part of the issue is, the models, a given generation of models are good for X, they're not necessarily good for Y, and it's not until you get out there and you test them that you find out. So I think, yeah, I would pick a middle course. I would say, how I would describe this is I would say, if the world worked the way it did in the model, then we could say this is what would happen, but that's if and would. And then to the extent we believe the world is going to be like that, we would predict that it would. It's a prediction. Now, is it right? It's going to be wrong to some extent. How good is it? We don't know, right? And I think one in practice needs to look carefully at like, well, how well do I think that the situation is likely to mirror what's going on in that model? And to some extent, you have to kind of interrogate that. But you can a priori yourself to death. At some point, the only way to know is to go and get the data. Mother Nature makes the rules. Okay, she gets the last word always. And we can predict her sometimes, and she's wily, and we can't predict her other times. So I think we're just going to need a lot of trials of seeing what works and what doesn't. What I think we'll find is that a lot of these models are probably going to be really good at some things and really bad at other things. We'll find there's some things that are very easy to predict and other things that are not. And we need more experience to do that. And that's going to involve kind of doing these kinds of, let's make a prediction, let's test it out and see what happens, and find out. A lot of different
Take more questions, and I'll do a switch up.
Okay, I guess here and then here and then
I was wondering, is there a tutorial for if you're not using RIM, but like Turgan or Organ, how do you have a guide for that?
Not yet. The only one we've made so far is REMS. Because I made it and I decided to do it with REMS. But also it's a little more obvious with REMS what to do with it. But yes, like I think in the long run, it would be nice to have computational experiment tutorials for a lot of different things. So right now the only one we have is there. But the ideas are very general, right? I mean, once you see how it's done with REMS, there's no magic. I'm not doing anything very special. I'm like changing parameters and simulating. You can do that. You don't need me to tell you how to do it, honestly. So it's like Dumbo's magic feather. Once you get the magic feather, you can do it. So, but yeah.
I guess I have a maybe more broader kind of question. We ended yesterday talking about position lead, and that's more common or normative in certain fields or certain types of analyses. But we all have ontological and epistemological beliefs of how the world works. And it feels like, in some ways, doing in silico experiments, that might also be really important to knowledge, because your belief systems about how the world works kind of determines how you code certain rule sets, or those possibilities and those things could happen. And so if you, I guess I'm curious about.
Well, sure. It's a model, right? When we say it's a model, that's what we mean, right? We mean that it embodies a certain set of assumptions. And by the way, not necessarily things we believe either. I mean, no one really believes where things work exactly like any model. That's the whole point, is simplification of the world. You could pick other simplifications, okay, of course. Part of what we try to do, and part of why we spent 20 years working on stuff, is to find classes of simplifications that empirically seem to work, and that's a lot of effort. So we have been guided to these particular choices. That doesn't mean they're the right choices for everything or the best choices, but they accomplish something. So you can take other choices, and one of the things that's quite helpful about this kind of approach is that it's honest about what the assumptions are. It lays them out. You can look at the code. You can see what they are. You can try other ones, right? And in fact, that's another thing I think in terms of in practice trying to get ideas ex ante about whether or not something is likely to play out. A natural thing to do is do robustness testing. So you can take a particular model that says that, say, you're going to have an effect of an intervention, say a smoking intervention. You could say, all right, let's mess with that assumption. Let's mess with the social mechanism. Let's add one that this group has hypothesized it worked this way. Let's try it with their model instead. So let's build a model of their theory or this other group's theory. Or maybe I talked to people on the ground and they said this. Let's put that in the model and see what happens. And if you try it a million ways and you get the same answer, that gives you some confidence that's pretty robust. If, however, you find that, no, actually, it really makes a difference, okay, I have an ethnographer, they talked to people, they said it worked that way. If they're right, you get a very different result than, say, what this biomedical thing says. Okay, so that's actually pretty useful. It's now said whatever that difference in mechanism is going to make it, we would expect to make a difference in the outcome. And that might suggest we need to do more studies to figure out which account is more veridical. Or maybe we just put them head to head, we go out and do the empirical test. At the end of the day, nature will decide, right? You know, it's not a question of, well, who has the right position to know. We make guesses and then, you know, we'll find out what happens when we go out there. And that, especially if you want to actually affect health, you know, you've got to go out and try something and then see what the effect is. But what these tools are not magic. What they do is they give you a way of, in a very sophisticated way, but a way of working out what are the consequences of assumptions. If we make these assumptions about how the world works, what does it imply? And we can make different assumptions and see what those different assumptions imply. And again, all that's what theory does, right? And that's all that theory does, but it's still pretty powerful. It is not a substitute for going and actually finding out. And I think we can get danger. I have had colleagues that I have a lot of respect for, but they get a little overzealous about the modeling things. Like, we don't need to do experiments anymore because we're just going to use models to do that. And that makes my skin crawl. And it's not just a social science thing. I mean, Biophysical Society a few years ago, this thing called AlphaFold that anyway screws up a lot, but people pretend it doesn't, but predicts protein structures. And I'm in an audience, and there are people actually arguing, well, we should just stop solving protein structure. We stop taking data, because we'll just use AlphaFold to predict everything. Or worse, they're saying, well, but people, when you publish an X-ray crystal structure, you should have to validate it against AlphaFold. So that is, you're going to take the model, and if your experiment disagrees with the model, you're wrong. That's left the path of wisdom. Okay, we don't do that, right? I mean, you know, empirical world has to win. But this is one of the tools we can use to try to get past. I mean, part of where I think what lies behind, maybe if not what you're directly saying, what others have said in that vein, is that we want to get past a world where someone just says, well, I'm an important person and my intuition is it works this way, and so therefore that's how it's going to work and we're just going to go out and do it. And we know that doesn't work very well. And so this is a way that you can say, okay, here is a way somebody might think, and we can see what follows from that, but we can try out other ones and we can see what follows from those others. And we can put them all on an equal footing and we can see how it plays out. And so I think it's actually a very useful tool for getting at the kind of things you're talking about.
Does the tool work for two-mode networks?
You can set up two-mode networks with REMS, yes. But the general ideas I'm talking about you can apply to anything, right? Any kind of model. I talked about REMS a little, but there's nothing very specific to REMS, right? You can use all these ideas with any kind of modeling approach that you can empirically calibrate. That's what's important.
Is there any special considerations we should consider when we're using it?
I mean, that's a long story about, yes, when you model things, you have to care about it's one mode or two mode. But I mean, in terms of the core idea of doing, experiments, the logic is the same, right? No matter what it is, really. I mean, you can do these. The logic I type of data, you can apply it to regression if you want to. I mean, it actually doesn't depend on having a complex model. It's just more relevant when you have a complex model. Right. Back.
So the answer might be the same sort of use theory and your limits. Let's say the classroom example, for example, like if you turn off social influence and then you find some emergent feature that's born out of the structure of the classroom, that's great. Like then you're excited, not necessarily unexpected thing. But let's say that you turn off social influence and everybody goes on some isolated nodes. But in the world, in the distribution of how classrooms look, there are no classrooms with isolated nodes. So you might expect, for example, that there's some sort of threshold at which people are like, I refuse to be by myself. Regardless of social influence, I will become contrary. So that got me thinking, like, what is the value? Have you found value in bounding your experimentation within the sort of like limits of the empirical world? Because after those limits, you're not sure if the model that you have, you're always saying the model might be good or bad, but it may be particularly bad.
Could be. Well, it all depends on what you're trying to achieve, right? I mean, so in the case I talked about, we're talking about a hypothetical counterfactual that is it's a Gedanken experiment, right? It's not something that we can really do. We can't turn off social influence. Humans are human; they're going to do that stuff. You can't make them not do it. You can't turn it off completely. But we can say if all of the other mechanisms were as we think they are, and you had some kind of robots, if you like, they're not really human, that behave that way, what would it do? And that gives us gives us a point of comparison to understand what the humans are doing and what the role of influence is in the system that we actually see. Now, in that statement is a statement about a model. It says, if the world works the way we think. Now, does the world work the way we think? Is the model right? Well, that's a whole other question. How good is it? And of course, yes, like the model, as you push past the limits of where it's been calibrated, right? It may not be a good reflection. But of course, that's that doesn't change the fact that what I'm saying is still a statement about the model, right? If it worked this way, this is what would happen, right? And that's the thing you always have to remember in your head. The mantra is that. Now, depending on your goal, is that an interesting question to ask? I submit that to get insight into something like fundamentally in a school, like say in those ad health schools, would we think, given that we think these models credibly reflect some approximate view of reality, do we think on average influence is having a protective effect vis-a-vis smoking, or is it seducing people to smoke? I think turning off influence is a pretty insightful way to get an idea about what's going on. Not that we think we could do that, but because it gives us a point of comparison that helps us understand what is the role of influence in that system. We're seeing in that system, it's actually suppressive. Okay. Now, for other purposes, of course, if you're going to say plan an intervention or something, then certainly you're interested in calibrating things within the realm of what's observed. And you might need to have other data to get that. For instance, it might be useful to look at a range of, fitting things to a range of schools, saying, okay, what is the range of this covariate that we usually see? And then if we're going to talk about extrapolating to what do I think might happen in a new school, then I think we might want to simulate, okay, what's a variation over ranges that we observe? And actually, I think that's something that's a very useful potential a function of this type of approach, is to say, okay, if you're going to go out and collect new data, what range of outcomes might we expect? And we could say, well, we don't know, but we can look at the range of things that we've seen in the past, and that could also include varying the demographics of the schools, varying other features of the schools, as well as varying social mechanisms. And we could say across the range of, say, demographics and mechanisms we've seen before, what's the usual distribution of outcomes we would hypothetically expect to see? Now, will that happen if you go and get a new one? We don't know that, but at least it gives you some ability to say what you might expect given that range. And then that creates a whole new really interesting set of questions about how do you bracket that range, right? Because to do that, you need models that are comparable. You can't just read off a coefficient, right? There are all kinds of questions that raise up. And guess what? It's a research area, right? So there's a lot of questions to be asked about what's the most effective way to do that. How can we best bracket ranges of reasonable effects? And I think that itself is a really interesting research question, right? And rather than just getting at, well, we see significant effects for X. Only for Brontosaurus, you saw a significant effect. Okay, that didn't tell us much of anything. What's the range of strengths that we have? And then what is the range of effect that has on outcomes, right? Those are questions that are more productive, I think, in practice. And, being able to model things gives us a way to think about that that's concrete. But there's a million questions like that we might answer. The answers are going to be, it's going to depend on what you want the model to do. And so we always have to come back to what are we trying to accomplish.
Awesome. I think we've for a non-morning person, we've taken too much of your time.
Thanks to all of you for your questions.
All right, so given that we've gone a little bit over, I'm going to take a poll of the room. Who would rather take a coffee break, bathroom break now, and then do some things, sort of get up and move around, so maybe, or rather sort of listen to me for another hour, then take a break? Let's take a break now. Let's do that. Great. So now, we'll get set up. We'll come back and some other things. That's awesome. I can listen to you all day.
That's very kind of you. I think our students might have a different.
Well, they have. Is the room mic working? Apparently not. So that's the auto answer to the question. So let's try putting up a little bit more. Can you hear that? Is that too much? All right. Okay, folks. Welcome to the end of the end of a long week. If someone can grab that door so we don't disturb our neighbors too much. Is this? This is not showing. Why is that not full screen? All right. Before I jump into this, first I want to, because I know people have flights to catch, they're going to be leaving and all this kinds of things, a couple of basic housekeeping elements. First, again, a large thanks to IID. Don't leave yet, Gabe. Thanks to other to the NIH for funding this, and for NSF PIP, who has also kicked in a little bit of money to help us sort of pay for our lunch. So we're really grateful for all that work, and we're grateful to everyone who's made that possible. We're also very grateful to the RAs, for Gabe, and to Madeline, who doesn't seem to be here. But where'd Madeline go? Anyway, when you see Madeline, say thank you. When you see Gabe, say congratulations. He finished his PhD. This is last year with us. And he is about to take a job at Indiana with Bria, working as her postdoc for the next couple of years. So double congratulations. So thank you for that. As long as we're in the process of congratulations, Carter, it turns out, just won an award for best paper for the mathematical sociology section. So congratulations to Carter. So that was just announced today. Other practical bits, we will be closing down at the end of the day today, so please, anything that you have, love, care for, make sure you have it, because we're gone, and so we're going to have a hard time getting it back to you. If you're here in any way on our dime, please get us receipts as soon, as fast as possible, because the grant year ends on the 30th of this month, and we need to get those in before that is done. Or it's just in the current, you get it, right? Just don't make me go ask the program officer for an extension. I don't want that. So let's do that. And otherwise, I want to thank all of you for all the hard work for this. And remember that this is a community, and so we should continue with that community. All right, so let's get into why we're here. The plan today is to talk a little bit about, the title of this talk was, I think was called Advanced Metrics. We've been emailing about it, it's a deep dive. It's a little bit of a bait and switch, I'm honest, because I started doing this. I started sort of putting together all of sort of standard metrics, and then sort of blowing it up, and it was just too big and just too boring for the end of the day. So instead of a network deep dive on specific networks, we're going to sort of just spin it a little bit and say, how do we find, create, and think about network metrics, right? So if you care about this kind of thing, it's a little bit more like what Craig was talking about. Let's get weird and see what we can do in the process of doing that. And so I'm going to do it first by sort of walking you through a set of ideas and a set of practices, and then a set of deep dive examples about how networks and network metrics work. And so what is a measure? Let's just start there. A measure is a tool for thinking. It's a way for us to understand the world a little bit and take these things that are incredibly complex, multidimensional features, and find some aspect of it that matters, right? For whatever the process is we're thinking of. So fundamentally, a measure is a tool for thinking, and we need to figure out how to go about thinking with that. So how do we do that? Well, the obvious things we do is we read. We spend a fair amount of time reading and talking and arguing and going to workshops like this, and we get exposed to what's out there in the world. Because all of us are brilliant, and some of you much more brilliant than me, but the point is that our brilliance alone is not enough. We have to go out and figure out what's going on in the world. And we've gotten a lot there. This is what you've done for the last 4 days, and for many of you for many years prior to coming here in the field and in the practice. And so doing that reading is important. And for me, my reading, just for a little bit of a personal history, these were the 3 books that sort of kicked me off in this field. And the story you're going to hear today is much more linear than the actual story to follow up on Carter's asterisk. But when I was going to graduate school, it just so happened that at that time, Wasserman and Fast came out. Almost, it had come a few years before I got there. I'm not quite that old. But have you ever seen this book? How many have a hard copy of this book? I have 3 hard copies of this book. One in each office and one I carry around with me. It is 4 inches thick. It is a big book. It is literally 900 pages. And I've read every one of those pages, right? That's what it means to read, right? So sit down and read and work it. And one of the things that I did when I was, some of you I know well, I'm sort of in your stage, I found an error in Sam Wasserman's book. Because I didn't trust me, so I was coding it and working on it. Frank was there. And so I scared to death. I showed it to my advisor. Peter said, well, I don't know, call Stan. so I sent it to Stan, and Stan goes, yep, that's an error. And we've been best friends ever since. And it's like, because he recognized the amount of effort it took to get there and to figure that out and find this thing in the middle, which is, it was not an error in the book. It was an error in a paper from the 70s that got transferred to the book. So it was a long series of things, and it was a deep dive into reading. And so that was, for me, the start of a certain way of thinking about networks. And then I had the advantage, because of who my advisor was, of really getting a chance to read The Anatomy of Kinship, which is Harrison White's really sort of most structural book, I think. It's the book that where you really take this notion of roles and ideas and you play it out through a series of relations that we all think we understand, but the implications of which we have no idea. And then I stumbled across a copy of Graph Theory by Frank Harary, which helped me understand that there was this entire field out there that was not sociology, not a bunch of sort of soft-headed, social sciences, but a mathematical, rigorous field that had built on this work. And they had proofs, and they had things that you could know for certain if you believed that other thing. And what a tool that could be. So find these might not be the books for you. I don't know what your books are, but find these books and read them. Go to the library. And why do you read? Despite all that reading, or sort of in the middle, but this is a much more linear story, I got really excited, still am excited about triads. I was reading Hollinon's work on sort of social structures and so forth. And I thought, these things capture what people do. They capture roles. What if we were to take these triads, decompose them, and use it to figure out who's the same? We have a quick way of doing block models. This is brilliant, right? I'm going to do this, right? And by doing it, the laudings will come to me and everything will be great. It'll be nice. So I went to work. I started going at the numbers and doing the work and coding and coding and staying up late night and mainlining coffee and doing all this work, all the thinking of I'm getting here. I am going to do this. I'm going to make my chance to change the world. Then I went and talked. As it turns out, in the classic sort of wonderful way in which your graduate experience goes, Peter had brought Harrison White down to Chapel Hill for a visit. The one and only time I had met Harrison White, and I'm scared to death. And I have a chance to talk to Harrison, and he says, well, what are you working on? And I says, I'm working on this. And he goes, oh, well, you probably ought to go read a book. I go, well, what book? And he goes, read this book that's already been published by Ron Burt on detecting role equivalence, which did literally exactly what I was going to do. That sort of sucked. Off you went. No more for that. So as we said yesterday, right, the point is to push it up the hill, right? You do this work, and we like the work. I learned a lot doing the work, right? But you got sometimes pushing that boulder is awful heavy. So read and keep reading and keep reading and keep going. And so what are we reading now? Where should you start? There's a whole series of things that are happening. One idea in the world right now is coming out by Zach Neal, which is he's proposed a network metrics sort of inventory and a regularized way of doing this. This is a thinking that what you should do is co-opt things that people know and make it out there. And it's a good chance to read, I think, in terms of, the theory here says, how do you read broadly? Well, this is what Zach Neal thinks are the metrics that matter. He has a list of them that he thinks should be part of everything you ever publish. It should be the same thing that you put in a published article, just the same way that you wouldn't eat a piece of food that doesn't have this on it, right? So if you're going to do it, it allows for comparability, replicability, and so forth. I think it's a good idea in theory. Adoption is going to be a real pain in the ass, right? And so I don't know if it's ever going to do it. But even in the course of this, in terms of putting together this presentation, I thought, wait a minute. One of the options he wants is a thing called global efficiency. I don't know what that thing is. I haven't heard this number before. I looked it up. It's the average of the shortest, the inverse of the average of the shortest geodesics. I hadn't thought about this number before, but it kind of makes sense. That's fun. So you will learn things by engaging with what other people think is important. So I think that's worth doing. The other place that seems a little pedantic is you learn a lot by using tools. Right now, all of us tend to go to R. That's sort of the new thing, or Python, or these sorts of things. The problem with those is it's kind of like the difference between searching for an article where you think you have an idea and you put a keyword in and searching it, and going to the library and looking at all the books that are next to the library that you want. The beauty of UCINet, which is not that it is arguably the most comprehensive metrics package still in the world, package program, is that everything is next to each other. So when you decide you want to do something like a triadic analysis, you're going to see that, well, next to that, what is a Zimalian embedded tie? What is the geodesic cube? I don't know. Go look at it, right? Go to the help files, read the reference, and then sort of go on these deep dives. And so you can engage with your work as you go to learn about things that you're never going to learn about. Similarly, you learn from each other. This is not an isolated sort of man-on-a-mountain process. This is an interactive process. And I had not heard of Tom Valente's alternative distance measure until he mentioned it in his talk yesterday. I thought, well, I should have learned it. I should have known about it, but I didn't. And it actually looks kind of cool. So he has these two measures. I'm going to give it a look. I'll see if I can use it. But that's part of the process, is that you have to go through and find these things. Read widely, review widely, read outside your discipline. There's a brand new work that Scott Feld and David Krackhart, I'm working with a person I don't know, sort of has come out with as a global measure of networks that is very closely related to degree assortativity, but different just enough, and they argue makes a really strong conditional for whether or not you can use the friendship paradox to generate an intervention. That is, this idea that you go out and instead of sampling the whole network, you ask people who their friends are and you sample that person because on average that person is more popular than the person you sampled initially. Well, that turns out that that strategy only works under a certain set of conditions. And they've come up with an index to help you figure out whether your network meets those conditions. That's kind of cool. So there you have it. So this process is interactive, of moving between thinking about network structure, doing the hard work and reading, and you're going to go back and forth between this lots and lots and lots. An example for a metric that I care about, which I'm going to sort of walk you through this story, is that I spent, just happenstance, I was reading at the same time 2 books. One of these books was Durkheim's classic Division of Labor, where the question is how our society is held together. What is cohesion and where does it come from? The other book I was reading was The Adolescent Society. I wasn't reading either of these books because I want to. I was getting paid to read the latter, and I was taking a class for the former, right? But this is what I was doing, right? They were both in my head at the same time. And so I thought for a second, well, what is, in fact, the analytic measure of cohesion? And so if you go from a Durkheimian point of view, we can think about what cohesion is. It's a collectivity of cohesive, a collectivity is cohesive to the extent that the relations of its members don't fall apart. This is what we were able to derive from a Durkheimian point of view. And we thought through a series of bits that sort of derived what this might be. And we can then go through and really think about, well, what's the intuition of Durkheim? If you have an anomic society, nobody's connected to each other. It's not until we build relations with each other that we get cohesion. But it's not enough to have a little bit of cohesion. We need to have a lot of cohesion, right? And it turns out that that ends up being complicated in lots of ways, because if you concentrate cohesion in a single person, why is this going so far, that doesn't do it. It turns out that the volume's not enough to do it, because if I rearrange ties that hold volume the same, the connectivity goes away. And so what you're doing is you're playing these games back and forth with your mind and thinking about what could be the thing that does it. And then I remembered that there's this stuff coming out of graph theory where we have the idea of node connectivity. And this is what the advantage of having read Harari and having worked and talked to, so it's a guy called Doug White, who was really the first guy to have this idea. And so we were talking together and came up with this notion that we can array cohesion across these different sets, and that's what gave us this notion of structural cohesion. That's where that idea came from. So this metric wasn't something that I invented out of the blue. It came from conversations with Doug interrogations with classic social theory, real social problems with ad health. All of these things combined led us to this notion that classic ideas of cohesion, simple density, weren't sufficient, but these other things could do it, and that had knock-on effects that I want to get to in a second. So the adolescent part of this was, well, if we're really thinking, or sorry, the flip side of this is that if once we have a measure of cohesion, we might also then think about this sort of combination of this idea of economic research that I was doing, because I was working with Arnie Kalleberg at the time at UNC, and thinking about block model. And so in the economic sociology world, there's this whole literature on embeddedness. Embeddedness is a rotten concept, right? It's a beautiful sensitizing concept. Like, we think about it, but it's a magic word. Measuring embeddedness, figuring out what it actually captures, is in the eye of the beholder. Like, embeddedness is sort of a term you throw around when you're not quite sure. Like structure in sociology, you throw it around when you need it, and it plays a magic role. But if cohesion is this thing that's holding us together, and embeddedness is how our relations, our social relations, make us less than a market sort of society, would pull us together somehow, then these two ought to be related. And how are they related? Well, they're related by the depth with which people are socially cohesive. And it turns out that this mathematical measure we had is really rotten at describing an entire system, because the entire system is always not cohesive, because there's people on the edge. And because there's people on the edge, we can think, well, this part's not cohesive, but this part is more cohesive, and more cohesive, and more cohesive. And it turns out that this measure naturally gives us a sense in which our relations not only tie us together, but tie us together relative to where everyone else in the network in a manner that matches really nicely with Granovetter's structural notion of embeddedness. Now, Granovetter has a second measure of embeddedness, or a notion of embeddedness, which is a dyadic version. This does nothing for that directly, but the notion of being embedded in a social system, meaning that it's hard to pull me out, is the mirror image of this notion that cohesion is this thing that doesn't fall us apart. And so again, the idea brought us to the metric. So we do a bunch of work, we stay up late at night, we publish a paper, and things go fine. Now, it turns out, of course, that this story is a fiction, like all nice myths. This myth, I've told it thus far as a story of our hero, but our hero never works alone. Our hero works with lots of people, and that's the other way you get ideas, is through collaboration. And once we published this sort of set of work, Dalia Mani came out and said, hey, Moody, perhaps it would be a good idea if we actually applied this to real large-scale economic systems, and we were able to map the entire structure of Indian co-ownership by thinking about cohesion and embeddedness. So we've taken the informal notions of embeddedness, applied the formal notions of embeddedness in the economic context, and we're able to do something kind of fun with that. So that's one way of getting it. And if you think about what that strategy is, essentially what you're doing to find metrics and to figure out what you should measure are finding problems, taking ideas from different places, and pulling together. This is a classic notion of recombinant insights. You take an idea from one side, an idea from another, you merge them together, and you get something greater than they originally were. This is, if you haven't read it yet, there's a great paper by Ron Burt called Structural Holes in Good Ideas. That's exactly the notion, that you're taking ideas from different places. The other place that ideas come from is when you see a problem, but it's a hard problem, you can't quite crack it. You're looking, you know there's something in the box, but you don't know how to get at it. And so everyone's sort of seen this image. This is the famous image from this paper. In fact, that's not what those networks look like, for the exact reason that Carter said just 2 minutes ago, right? Because those sexual relations in this high school didn't all happen at the same time. I love to show that first picture to parents. It kind of freaks them out, right? I don't mind doing that because I don't have kids, so I can laugh at them and say, there you go. But in fact, real relations look like this. They come on and off, and they unfold over time, and they have all of these issues. And we're selling ad health, and we're selling this process to think about disease flow. And so the real question is, how the hell does disease move through this? I know how things move through this. This is easy. I can just trace a path. I can pull up my Harari, and off we go. This, not so much. It's a real hard problem. And it's a real hard problem in a way that just requires us to think, and to futz, and to play, and to think, and to think, and to think. And nights and nights and nights, we're just pushing the thing up the hill. And you gotta love it. You gotta love pushing the boulder up the hill, because it's all it's gonna get. And finally, we broke it down into this notion of early and late. That what was really happening when you think about what constrains the flow of something through a network is that when I have it, I'm interacting with people when we're together, and I can't interact with them later. So there are some things that are before you, and there are some things that are after you. The relations my partner has with people who, with people other than me after we're together might break my heart, but they're irrelevant to me from a disease standpoint. The relations they've had before me, I need to be concerned about them. So this pre and post was the idea that we were thinking of, and it turns out when you think carefully about that the network that we're used to seeing actually has this set of implications. And I've talked about this a bit before for those taking this class, is that you can imagine that things that are early to late, before and after, and then after and before again, that's a stop. So for each straight, you end up with this pre and post ordering sequence. And if the sequence is right, then the disease could flow. And that means that every network that we think we see is actually 3 different networks layered on top of each other depending on how you think about the timing. There's a contact network, an exposure network, and a transmission network. And the actual risk set in this network is very, very small compared to that giant thing. In this case, this is not a graph like you're used to looking at it. This is an implication graph. This is the largest set. If there's not a line between the 2 of these things, they can't infect each other. So in fact, it's the case that somebody like these folks, they're in the set, but because all of these relationships happen later, later, none of the stuff that's going, or these relationships happen later, none of this work can flow into them. There are breaks on either side of it. And each of these little clusters are spaces where disease could possibly flow, but none of the spaces inside them can. And so this allowed us to see it, and we did it by thinking through this idea and coming up with this, in conversation and spending and putting in the time. That's all it is, right? But once you have this, then you get everything that comes from that. And that's the beauty. Because once you have that, the real recognition here is that paths are no longer simply additive. The graph theory paths that we're used to doesn't work the same way. So it turns out, for example, if you want to think about what the shortest path is in a network, it turns out that A can reach D in 3 steps. And from a graph theory standpoint, if D is connected to E by 1 and A is connected to D by 3, then this should be 4. But it turns out, in fact, that it's not, because we can go this way. We can go around this set. So once you understand that path structures change in a network once you consider timing, then everything that follows off path structures change if you consider timing. That's both frightening and exciting, because now you have the opportunity to think about everything other measure that you've already thought of, every other metric that you're used to, now has a variant on a timed graph that could itself be interesting. So for example, we can think about temporal reach. We can say, is it possible to reach someone else through times? This is what Martina Morris and her colleagues recently referred to as forward reachable paths. It's possible for me to reach you on the other side. We can also have sort of the temporal geodesic and the temporal paths, which is the same sort of ideas, but we could also make duration explicit measures. We could say, well, the quickest path might be different than the shortest path. There might be a way that a long number of steps across a really quickly unfolding sequence would be faster than 2 long monogamous steps. And so there's a difference then between these things. And you can go through and define a whole series of different measures that are taken on the temporal geodesics or the temporal distance measures as opposed to the underlying graph structure. And so this is a way of generating metrics by taking an idea you have from solving one problem and then just morphing it to solve another problem. The other idea we had with this is to think about some tricks about this relationality. The real thing that when you think carefully about these timing sequences, and these are timestamps on edges, is that if we're really caring about earlier or later of the edges, the nodes become somewhat irrelevant. Right? The nodes are no longer the thing that's really driving your concern because nodes are merely adjacent to ordered edges. So why not flip it around and use what's known as a timed line graph? And I thought I had an image of it here that allow you, that's just out of time. Oh, sorry about that. Anyway, you can flip these around. Yeah. You can flip this to which is this thing known as a line graph. And in a line graph, every edge becomes a node that's connected to another edge by sharing a piece. And because they're ordered in time, it becomes a directed graph. So a directed line graph allows you to see this outcome much better. So the basic idea is insight comes from identifying different sets of sets. The third sort of notion that where you can get new ideas is to think about debates in the field. Right? A lot of what we do is argue with each other over things, and there are some people who are, this is their key source. Find a fight and figure out how you can solve it. I don't like to fight. The reason Peaceful Thoughts is in is at the footer of my thing, is I find I'm a fight avoider if I can help it. But it does help. If you've done this other work and there's a fight out there in the world, you have an opportunity to say something about it. And the fight that we were engaged in at the time, or cognizant of, was, does concurrency change the likelihood of HIV epidemics? Big fight. And the reason it's a fight is because there's a logic to it intuitively that Martina Morris came up with when she first started this, and some works that she did in simulation, in silico, as Carter pointed out. And then the regression analysis, looking at different countries with different rates and finding very low correlations. It's like, well, that sort of sucks. We think it works in the theory. We go out and test it in the way you would normally test it. We don't find a solution. What's going on? So when we came up with this timing type of stuff, this way of thinking about relations that work together in timing, it allows us to decompose when it's possible for a concurrent relationship to matter versus when it's not. And so we do that by imagining lots and lots and lots of different social structures, and then asking, is it the case that concurrency matters more in some kind of structures than it does in others? And so we did this as an in silico experiment, just like Carter said, and we came up with some ad hoc measures, which sometimes your metrics are ad hoc, which is to get around this really complicated structural cohesion problem. We just said, well, instead of finding some way to capture the pure nestedness, let's see if we can get any juice out of an easier lemon, which is just by averaging the pairwise cohesion in the network. And so we can do that in different ways, and you look at the connectivity in these networks, and it's fine, right? You end up, it intuitively matches. We get sort of much more cohesive networks here. They have a higher value on this connectivity score than do really sparse networks. And so let's generate a bunch of networks, let's actually find a bunch of networks that have this kind of structure, and then compare it to and then manipulate the amount of concurrency that's observed in the network, and ask whether or not we find an effect that differs by the structure. And you really do. It's a very strong effect. And what's happening here, effectively, is that when you have very uncohesive structures, you have no loops, you have no ways around the network. And so the timing really matters. And so just like I said the other day, you saw this graph, that's where this idea came from. The structural cohesion idea attuned us to the timing idea by thinking of the ways in which the structure essentially undercuts the limiting features of the timer. And by doing that, you end up being able to resolve this debate by noting that we shouldn't see an empirical correlation at the level of the country or the level of the network between concurrency and disease size. Because some countries are going to have lots of local loops and concurrency is going to be irrelevant. Some countries are going to have other sorts of sparser structures in which concurrency is really going to matter. And so the macro return to concurrency is conditional on the underlying graph structure that then makes the timing more or less relevant. And that's because timing is effectively a diffusion process that's conditional on local loops. You have to have these local loops. And the local loops don't matter if you already have global loops in the network intuitively. And so that's one solution to this. And we were still fighting it. This is still an argument that's ongoing. But the beauty of this kind of modeling is that we can now know really well. We can write down and show very clearly that something like concurrency is no different than birth rates and demography. That I can have lots of different countries that have different birth rates and different population sizes and different growth rates, even if they have the exact same birth rate, because they have different death rates or they have different migration rates. But it's necessary. There's a necessary relationship between births, deaths, and migration to generate population change size that can't not be true. And the beauty of things that are necessary is that same thing is true here. So if you're not finding what you think you're finding, but you have a necessary relationship, then that necessary relationship implies you should be looking for something else. And that's the kind of hard problem that requires you to do a lot of sleeping and working. Well, there's the plot points I thought I had. So this is, now I've taken this graph, which is the timed edges, and turned it into a directed temporal line graph. And so now these are the edges in the original graph. And if one precedes the other, you get an arrow from it. And if they precede each other, if they're concurrent, it pops out as a symmetric tie. All right. So what's the point? Why do we do this, right? We spend a lot of time working, and I think that many of us, especially when we come into this business, we think the reason we're spending all this time and energy doing this work is because we want to do something great. We want to affect the world. We either want to, cure disease. We want to get a Nobel Prize, right? We're doing it for extrinsic reasons. That's possible. That's one thing we could do. I think that's a mistake, right? You have to hope that you have extrinsic rewards. But the intrinsic rewards of pushing the ball up the hill have to be there. It has to be, that Sisyphus is happy just pushing the rock. And if he is, then Sisyphus will be able to keep adding to the collective benefit of the things we do. One brick at a time in a large wall of knowledge. Sometimes you knock a chunk of the building down because you discover something that no one else does. But if the process itself isn't keeping you up and motivated, then you're going to have a hard time doing it. So my thinking is that Sisyphus is happy, and you should be happy doing it this way. So, I told you it was a bait and switch, and I apologize for that, but I'm happy to answer questions on either the ways in which we get to new metrics, or actually if you have a real metrics question, I'm happy to answer that question as well. Please, Carol.
It's not a metrics question, I'm sorry, Jim. But
That's
I'm
good.
thinking about, the nature and the quality of data, especially, data that are subject to social desirability bias.
Yeah.
And like Nancy Luke so many years ago right here at Duke developed like a relationship history calendar that they used for that pop muscle project that we like adapted and used in our studies. And it allows people to like just chunk out and sequentially talk about relationships in context and using it that calendar method to kind of get partnership, sexual frequency, all those things, without kind of directly asking the sensitive question, how many partners you're sleeping with.
Yeah.
And it really makes a difference in terms of what the data show. And people have kind of validated different ways of collecting data on sexual behavior. And you already see, if you just move from qualitative data collection to quantitative data collection, there's a difference. But there are methods to improve the quality of data that have big influence on kind of these empirical questions. And there are techniques like conversational interviewing, where you're doing a survey format, you have closed-ended responses, but you're using conversational or qualitative interviewing techniques. So there are ways to improve data quality, and I just think sometimes that's underappreciated.
Now, I 1,000%. I think that these problems are hard problems, even under the assumption that you have good data, that the data is pristine. Then you recognize the reality of real life data collection and all the noise that's put into it, and not even the noise, but the systematic distortions that come out of these kinds of things. It's remarkable. And I do think it's really easy to undersell the work that data collection is, and also the implication of what we might think of as academic models. Because if it's the case that concurrency is like birth rates or migration or something like that, which I think it is, and I think I can prove that I can literally prove that it is, then you do no harm from a disease sort of constraining set by saying, avoid concurrency. right? We don't need the evidence to show it, right? But we can, and so, so I think that the debate of, so once you know these things, right, unlike a simulation or anything else, you have the ability to make predictions in the world and do changes in the world that are useful, right? And then we can think about what's the best way to make that change. What's the most sensitive way to make that change? What's the most effective way to make that change? What's the way to do it without incurring some other knock-on effect that we hadn't thought about, right? So then the question doesn't because should we bother? It's like, how's the best way to do it without sort of creating something else that's going on, which is going to be a cycle as well, but that's my question.
Yeah, I have this kind of lingering or ongoing frustration in environments like this of like, I really appreciate your comment about qualitative data collection because I think it's so important that we do this and improve the quality of our data, but there's also like, I've just heard over and over again this week, and then I thought it might be this, so I tested it, and it was never, and then I talked to my subjects, and they said it might be this, so I tested it, or like one or two people said that, but that's really not the way these questions are being formulated, and similarly, there's no harm in saying avoid concurrency. There's no harm in saying be abstinent. It's the best way to prevent transmission, you know, but it's harmful, it's super harmful. So my question is like, first of all, I guess what's your take on it? This qualitative question is like why are we so afraid of qualitative data? And second of all, what would you recommend to a young person who's like, I want these conversations to shift. I want more people to be thinking about.
Yeah,
So
so my take on this is that science is a division of labor. That you can't expect people to do everything simultaneously. And so people who are good at talking to subjects should talk to subjects. People who are good at talking to computers should talk to computers, and those two people should talk to each other. Now, I think that a frustration for people who are really good at going into talking to neighborhoods is that why don't you just go talk to people? It's because, why don't you just go program the damn thing, right? And so I think that there is, and the key is that science is going to fail either way. I mean, the problems with qualitative work is rife. Like we could spend an entire week talking about the dangers of qualitative work, right? The myopia, the projections, or 1,000 of the things that could happen. But that's useless, right? The point is, and it's also myopic, right? The point is that these things work together. They have to work hand in hand. If they don't work hand in hand, then what you get is tribalism, and you get my way is better than your way, and it doesn't create an advantage. So the advantages of having sort of the modelers work with the data collectors, work with the informants, is that you then have a throughput. Now the problem with it is it's slow, right? Because and I think that people who are on the ground, especially if you're convinced you know the answer, which you should be really afraid of if you think you know the answer, especially if you think you know the answer from talking to a certain small subject of voluntary subjects, you should be really afraid of the answer you think you have. But if you believe you know the answer, right, it's really frustrating to wait for the CM modeler to say, well, I got a bunch of modeling to do. I'm not entirely sure. The standard error is big, right? Let's let the reviewers look at it. And so the process is slow. Science is slow. It has to be slow. And if you're really frustrated with slow science and you really think you know the answer, then be an activist. That's awesome. Like the world needs activists. Go out and do it. That's great. And then you can do activism on the things you think are true, and we'll study it and see if we think it was right. Right? So I think that this is part of the ecosystem of knowledge production. Please.
I share this, so I appreciate you bringing this up and talking about it, and bringing these things together, but I just want to share one little hack I've been trying to apply, which is, including in my surveys, like, hey, what ties are not here that you wish were here? What ties do you really are burdensome to you? And this all comes out of my work with autistic people and conversation with autistic people and starting to understand the burdensomeness of networks. Like, why don't they just tell me what do they want their network to look like? And embed in your survey questions to the people that are participating with you that are informed by your conversations with your population. So you can just start to ask those questions, and then your modelers you can really tell them.
Please. Yeah. First Cara, and then Christina.
Sorry.
No, go ahead.
I feel like you know, it's relevant, obviously, that Facebook has changed as a platform so much now to the point that the work that was done in 2012 on emotional contagion over Facebook is not actually relevant to Facebook as a platform anymore because of all the changes that have happened on that platform. And I find that when I'm thinking of my research and doing my research, the folks in my field of developmental psychology, they're also so siloed in their, you know, ways of thinking, and, you know, there's a lot of people, like you were saying, there's tribalism of the, you know, the quant people and the qual people and the mixed methods people, and they also don't really talk. So I find myself in this situation where I've made it a real value of mine to listen to the people who are, especially from different fields, or I take things from, you know, folks who are doing qual work to inform my own research. And I don't know, I obviously, I just like to learn, that's it really. But I don't know, I don't really have any answers, but at the end of the day, like, I'm still constrained by like this nebulous, you know, I'm never really gonna have any idea what's truly going on social media unless the social media company gives me access to their algorithm,
But I'm gonna push back and put another plug in for searching for necessity. That the reason that, so think about the work we've done on emotional contagion on Facebook in 2012. Ask yourself what part of that work is necessary to humans interacting with each other online? What part of that work is contingent on what's being fed by the algorithm, and how you might know? Because the necessary parts, the human parts, probably haven't changed. Platform parts have probably changed. And so then you can think, well, what if, and the real trick, and this is what I thought was so nice about Craig's talk the other day, is that once you have that question, what is necessary about contagion of emotions online, then you're not dependent on the algorithm. You can go out and you can find variations in the way that algorithm works and see if that necessity is there and what it might imply.
right, yeah, maybe I wasn't explaining myself correctly, but like, yeah, that's my exact, yeah.
And so in that
I
kind of
probably didn't correctly explain
right, and so in that kind of situation, I think you want to ask yourself, you know, what can I know? Now it might be that the Facebook sort of world, or the whatever else that folks are working on, that the underlying algorithm is so dominant that there's so much signal from that everything else is effectively noise. In which case, you know, maybe do something else. Find comments in newspapers, something else that you care about. Or find a way to work with those people to the extent that you can. All right, Christina, you have it, yeah.
I don't want to be the dead horse, but like the whole quantitative versus qualitative arguments, right? Is kind of like the depth versus breadth kind of thing. Like I think they're both important and there's a room for both of them. The only issue is like that it seems like in academia there is a hierarchy of methodologies, and I like that it's a general skill, and I think that's where we kind of get peril. Like it's when like we feel like that the quantitative get like the less than.
That's what every historian tells me.
Yeah, but I feel like there is room for both methodologies, like, and there is room also for both understandings in social networks and otherwise anywhere.
I just want to offer as well with that, like Mario Small, I was really
Yeah.
intrigued when I found his work, and he is someone that was able to kind of break through without using a whole lot of outright quantitative things, eventually like using them, but like very heavy theory, like, and
That's a great,
Mario
yeah,
Small.
Mario Small, that's a great example, and Mario did it by, you know, doing all this hard work we just talked about here, but also he worked with Bernice, he worked with Bria, he worked with an entire department of other people that was on the other modalities of data collection, and in the process of doing that was able to, you know, think about these problems in different ways. And he's a ranked member, at least he was last time I was, of the methodology section. So he's not a stranger to this sort of to these sides of work. Please, Carter.
Another comment, this is something you guys have to think about as you look at your careers forward, and more importantly, you should remember years and years from now when you're in the very, some of these problems that you're grappling with, and people in the field, and frustrations you have, which are, of course, kinds of things people always struggle with, but some of them are not what you think they are. So you think it's a quantitative fight, you're like going back and talking to your subjects, and you think this is about methodology. It's not. A lot of it has to do with the cycle, the temporal cycle of science, and the time scales on which you can go back to things. So why don't people go back and talk to the subjects about something they're finding modeling? Because these things are separated by years of work, often, and also institutional barriers. And some of this is the result of policy. And I've seen the change in my own career. When I first started, unless you were doing health stuff maybe, but a lot of other stuff, you didn't have to do, most universities have hierarchies that govern human subject stuff. People came up with experiments, psych experiments, whatever. You dream up an experiment in the morning, you do the experiment in the afternoon. And that enabled a feedback process by which people could have ideas, they could test them out, they could then go back, they could go talk to subjects under certain saying, let's go ask people what's going on. And the cycle, the feedback loop was very fast. Not for all kinds of research, but for certain kinds of social research. You could do that. And so what has happened over the decades has been enormous streams of bureaucracy, put there for reasons that are very well intentioned. But now, if I want to ask people basic questions, it's going to take months of paperwork, right, to do it. I have 1 million people looking over every single thing I'm going to do, and it's got to go through all kinds of, and then to get the money to do all this stuff, So it's like, okay, you want to go back to your subjects and ask them something? Oh my God. In 2 years, if I get the money, I can go and do it, and then I can ask them something, which is probably not the thing we should ask. And so there are a lot of things that look like they are problems of method or look like they're quant problems or whatever. I mean, I'm not saying they're not in the dimensions, because there are, but some of these really just have to do with the fact that it's very difficult to do the back and forth you would like to do to say, I'm seeing this pattern over here, can I do a cross-check on it? Because to really do it, you need to do it quickly in real time. And then you're talking about the problem about, man, you study technology stuff, or some of the work I do is in that area. Stuff changes out from under you every minute. And it's very hard to keep up with it because literally the bureaucratic system won't let you do it. Now again, there are people who will defend those systems and say the world was a horrible place before them, and people could debate that. And I'm not going to say one way or another what's good or bad in that sense, but I want to say they have consequences. And so something you should think about, not for now, but for 20, 30 years from now, when you're in positions of authority, you may have, some of you in this room will have power over setting the rules by which research gets done, and setting policies, and that involves confidentiality, subject protection, whatever. There will be pressures, of course, let's have the most strict rules we possibly can for maximum protection, and there's arguments for that. But you should also bear in mind that the more walls you create, the more you make the enterprise difficult to do, and some of the things you're running into are also related to that. So we collectively have made choices about what we're allowed to do, how we're allowed to do it. And those have had all kinds of very far-reaching emerging consequences, some of which you're kind of experiencing, including further siloing different areas of work because it is difficult to do things, making it difficult to have the kinds of back and forth and crosstalk that you want to improve your data collection, to improve other things, because now it has to go through decadal time spans. We have entire areas that are kind of withering on the vine because we can't get new data sets, and why are we still analyzing ad health? I mean, my reviewers say that too. But because we don't have it, most of us don't have access to anything. I mean, there's just lots of challenges that we have that have to do with that. So, I mean, we're not going to fix them today. But what I want to plant in your heads as you go on in your careers is look at the problems and the frustrations you're encountering now. Understand that to some extent, some of them are eternal. Some of them are the Sisyphus thing. Some of them are the result of structures that you're in, and some of those structures you may have a chance to influence in the long term, and you want to be thoughtful about. When you have some influence, you want to have grand power or anything, I promise you, but you may have influence. How can you think about how the decisions you're going to make about policy are going to affect the ability of you young people, like you are now, to actually advance knowledge? And then, in the case of health, help people. Because there are trade-offs. There's no free lunch. But some of these things that you're seeing are actually the result of other systemic factors in some of these.
Elizabeth?
I would just amend slightly this, that we have solutions for this already that have been in place for a while. Mixed methods research models. You can set up your IRB from the very beginning if you have a multidisciplinary team that you have in place at the beginning of your study. And there are very rigorous ways to do this, but it's harder to win those grants, right? Because there's a lot of questions and you have to share funds, and you have to have a budget that can sustain everything. You know, so I would suggest that there are ways of doing what you're saying right now that are in place. And if you bring in the community model, then you can, bring in a rigorous way, community feedback loops. These models exist.
Yeah,
right,
you
already.
can't, however, they can help certain things in certain narrow situations, but they're not going to fix the bigger picture things that the time scales are off.
Budgets.
And budgets, and that's another policy.
Please, Carol.
Yeah, I mean, I have slightly, well, first of all, I want to say, Jen, to me, you're such a model of someone whose scholarship has been really productively, intellectually promiscuous. And I always, this is really what I advocate among all of my mentees, read, everything that you said. It's the same thing I say, read outside your disciplines and be stimulated and make connections with people who read outside your disciplines. And so that you can have the kind of productive conversations that you need to advance your engineering scholarship. So to me, you're like the math person who also read the ethnography, the ethnographic tradition of sociology, and that's just ideal for really moving things forward. I think multidisciplinary teams, not specifically necessarily mixed methods studies, but working in multidisciplinary teams is the ticket. And sometimes it really does work within the life cycle of like R1 and UO1 and other kinds of large scale projects. I'll give you one concrete example. We had bullying studies and medical research trial, test and treat trials, right? We had these enormous, community health campaigns. We had teams of researchers doing, participant observation at campaigns. They saw that crowds of guys were at the post test station, timing how quickly people moved through it to figure out, to infer who is HIV positive and who they should date, right? So we fed back the qualitative findings, put up privacy screens in post test stations, right? This got integrated in real time. There were things like that that happened through the kind of productive interplay of multidisciplinary researchers. And we want the biomedical, this is why I'm in medical school and in American medicine. I want the promise of biomedicine to achieve this. I want that promise. Even though those, a lot of us people think that the discovery of the product is the end of the story. Success achieved and everything else is, irrelevant. But of course we know you can't necessarily make that product ingested within the body and create change in the community unless you think about larger contextual factors and making sure that things happen in the most optimal way. So I guess I would say also connect with each other, connect with others. I'm here because I really admire you math people, and I want to actually be really stimulated by what I see you doing. So, I think also connect with the people who are in other corners of the university.
We're going to come back to some of these discussions in the future directions sort of panel. That's what this is. The future directions panel is exactly to think about, not panel, the discussion is to have these kinds of sort of what are the actual dimensions we want to work on as a field and as individuals sort of moving forward. So any other questions on the non-metrics metrics? And I'll jump over to community detection. Awesome. My machine died. That's not good. Where'd that go? The beauty of speaking, you're doing 2 talks back to back is that you can steal your own time without too much trouble. So that works out all right. Okay, what I want to talk about a little bit of time now is clustering on networks, as is my bad habit, there are many more slides and way much more here than you can ever get through in the amount of time I have. Because I'm running the show, how much time do I have? Interesting. But I'm going to spend most of the time today on community detection. I'm going to point you to some work we're doing on roles and some new tools we have for doing that. But just in the sheer interest of time, we don't have, I won't subject you to this. If you think about that little cartoon sitting on a computer terminal, drinking coffee late in the night forever and ever and ever, that is my relationship with communities and roles. This is I love it the way, I love a wayward child, I think. It's like, I can't not have it. I could write country songs about community detection that would probably be chart toppers. And for those of you that don't know, community detection is it's the Afghanistan of network methods. It's easy to get in. You're going to spend a lot of time there. It's hard to get out, and when you get out, it's not clear you found what you thought you wanted. So just beware, right, before you jump into this war, that you know what you're getting into it. And I think we've found some peacekeeping tools, if you will, to help make this a little bit sort of manageable. But it is it's a much more complicated problem than people think it is. It's a much more complicated problem than the way people use it is. And I think it's also, the flip side, a much more informative problem, because it turns out that it is a special case of a very general thing we do in methods that we don't think about. Because we do dimensionality reduction, we do clustering, we do latent growth curves. There's all kinds of things where we take buzzing complexity, make it simple, and we do it based on a heuristic and a decision rule. The only difference between all of that work and the community detection work you're seeing is that the community detection work didn't start with, someone didn't set a really hard heuristic rule of thumb that everyone then just adopted by fiat and went on as if it didn't matter. And so we've been questioning our heuristics and questioning our decision rules every day that we keep doing the work. And nothing about factor analysis is fundamentally at the level of a method different than walk trap community detection or the problems therein. It's just a different set of approaches to how we accept an answer or not. And so in that sense, community detection ends up being a much more honest data analytic technique, but it is also one that requires you to be a qualitative, quantitative sociologist. You have to be the kind of person that takes numbers and takes methods as an informative feature for judgment. And this is as much an art as it is a science. And we're going to give you now, I think we've come up with some pretty good paint by number tools, but we're going to hope you are still willing to recognize when you can paint outside the lines. So, what do we got? A little bit of background already. I hit on this idea just a minute ago. The reason you get into this work is because, like I said, if you can avoid it, avoid it. But if you can't, the reason we can't avoid it is that sociologists care about the meso level of society. We're not historians per se, very few of us. It's not, our goal isn't to understand the broad stripes of history and the narratives that guide those. We're not psychologists. We aren't trying to get inside people's heads. We care about that meso level between the individual and the society, and that level is a group. And the way those groups are structured and the way they're generated informally is the part and parcel of why we do this business, often as sociologists. And from a network and health standpoint, the reason we think about this as groups is that we have this hypothesis, a sneaking suspicion, that people are not substitutable, and their local relational context changes the way they view the world, changes the ways in which they behave with each other. And so these clusters actually have ontological reality of some sort that we care about that helps drive what we do. And it's a cohesion story, it's a heterogeneity story, and so we're kind of stuck with it as what we're doing. And so this notion that cohesive networks lead to different kind of feelings, that lead to different kind of social outcomes, that's one kind of model. We're not going to talk about any of that stuff today. So we're going to talk about just this idea of groups. And so the idea of a group has been pretty standard in sociology for as long as there's been sociology. So how should we think about this? The other sort of pathology of sociology is that we're ruled by the 2x2. So everything I do is a 2x2, and because I like pictures, I don't put text in my 2x2s, I put pictures. So here we go. So we can think about the problem of what it means to have cohesive groups and networks as really the intersection of two problems. One is a problem about cohesion per se, or what we've already referred to as node connectivity. It's how tightly held together things are. And the second is a question about boundary specification, how salient the boundary is between us and them. So I can have the cases where both of those things are really low. That's a market. That's a transactional society where I don't care who I buy from, I don't care exchange for, you're the type of person you are, so long as you have the good, we can get to it. If your price is right, I'm going to go to you. Right? It doesn't matter. That's the only thing governing here is exchange, and it's dyadic based. There really is no structure per se, at least in the short term in that way. When this is low, when boundary salience is low and cohesion is high, you get really integrated societies. You get sort of settings where, like the Whitey beaches we talked about, where everyone is connected to everyone else because we're engaged in each other through multiple dimensions. There's no my boat and your boat, or at least it's not strong enough to get over the fact that we need to be on boats with each other at different times for different fish or what have you. And so there's an integration across the entire system, and a lot of our other sort of features don't matter. Boundary salience, which is the colors represented in this graph, is the idea that there are categories of people that we engage with differentially from other categories of people. And when cohesion is low, and that's true, you get something like kinship systems, like the classic anthropological kinship systems of where do I get my partner from. And so if I'm in this tribe, I get my partners from that tribe, and so forth. And so you can think about moieties and other kinds of anthropological studies of kinship systems. That's what this is. So what group am I in? That determines what group I get my partners from. The cohesive group set is the intersection of both of these. It is not just that we have boundaries, jocks and nerds, but within the set, we sort of have some sense of usness, of relational density that creates a connection that reinforces that boundary. The beauty of this kind of way of thinking about it is that it turns out that we can by differentiating the boundary features from the cohesion features, we can then think about social processes and the ways in which they're sticky. That once you get from here, it's really hard to get back to here, because boundary salience reinforced by cohesion reinforces the absence. And so this is why integration is really an uphill battle, because these things tend to reinforce each other from a theoretical standpoint. Now there's lots of different ways to get at networks. The history of this work, and I encourage you to read it. It really is a fascinating sort of sense through the scientific process of trying to figure out solutions to problems. The early sort of work on this was coming out of graph theory, looking at cliques. It's not particularly effective because real life is too messy, but it's a good understanding. It's a good thing that starts what we're doing, because what we're effectively getting when we do cohesive group analysis is identifying messy cliques. Then we ended up with a whole series from about the 70s and 80s where we recognized that cliques and formal sort of connections were not good for this combination of modularity of boundary salience and cohesion. And so we had a series of really smart people come up with models to try to find patterns in networks. This work tended to be a little ad hoc. It was often very smart, but it was doing methods the way that people in the town that I grew up built houses. Every time you had a kid, you added a new room, and before you got there, we called it a ramble because the houses just looked. There was no architecture to these houses. Right? They're just what they were. But everyone got to sleep there. It worked fine. Everyone had a roof out there. So it was functional, but it wasn't beautiful, right? And so recent work has focused on sort of taking these general ideas and making them beautiful, or what's the architecture underlying it. So this is the problem we typically approach. We think about groups and networks. We're going to say, let's try to capture the networks that looks nice. And if your world looks like this, you don't need me, right? You can go in and say, look, there are the clusters. Look, they're already colored. I can go home. So if everyone's wearing, if everyone's wearing the right hat and whatever, then you're good to go. The real world, of course, doesn't look like that, and I'm not going to go through these parts. The real world tends to have not just these kinds of clusters and sometimes between them, but the amount of things that go between them, it makes it so messy that you can't quite see it. So how do we do this? The way we do it is that we first have to have an objective function. We have to have something we're trying to do. And so the thing that we're typically trying to do is to ask the question, well, I'm going to be really careful here, to impose on the network the best thing that looks like this. So what I mean by that is we're going to take our network as we observe it, and we're going to draw bubbles around sets of nodes such that the amount of density on the diagonal of these bubbles is much higher than the density between these bubbles. That doesn't mean the bubbles are really there. We can draw bubbles around anything. Right? So you just keep that in the back of your mind. And that's why you have to play with these things a lot. In order to do that, we need some measure of whether we have our bubbles in the right place or not, and that's the objective function that we're going to go after. That's the measure of fit. Once we have a measure of fit, then we need a process to figure out where to draw the boundaries of the bubbles. We need some heuristic to say that the bubble should go here or here. And that's where all the work has been, not all the work, but a lot of the work has been lately. The metric that there's a bunch of metrics that if you go to the slides, they're hidden here, and I figured I might be running out of time. So I'm going to focus on the metric that people have been using recently. It's this thing called the modularity statistic, Q. And there are different versions of it. And Q, I know we said the other day that no one likes equations, but this is not a complicated equation. And so I'm going to walk you through it because I think it's worth doing this one time. I promise. So we have the main thing you're going to do, if those of you really don't want to think about it, what we're doing is we're doing the observed minus what we think by chance. And so this is our observed adjacency matrix, so ties between people. That's the thing that we're summing over. So we have essentially a count of ties in the network. Then we have some formula, some model for random expected ties. Now this is substitutable. You can put lots of different models in here. The model that people typically use, the default one that's been standard recently, is a degree based. And so we have the degree of I and the degree of j divided, normalized by the number of lines in the graph. And so this says what's the random probability, row, column, chi-square style, of us being connected. And so you can see what this is, right? So this is the observed minus the expected. That is a chi-square. So that's just how much more ties do I see by chance in this set. And then we're only going to sum that up. This is a resolution parameter. I'm coming back to that. Ignore that for now. The rest of the field did, turns out, problematically. So for the moment, you can also ignore it, but we'll come back to it. And so we're just going to sum this thing up for the cases where we're in the same groups. And we're going to say, let's take the time when that process, so if I'm in cluster I or cluster J, or persons J or I are in the same clusters, C, then we count this. If they're in different clusters, we don't count it. It's just an indicator function. And so what that means is we just keep shifting which cluster you're in until this number is big. That's the simple as that. What could be easier? And we normalize it by some stuff. So Q is nice. It ranges from 0 to 1. It has no sort of inherent sort of cutoff values or things like this. So it's not like a t statistic or something like this. But it is a difference from random in that sense. Actually, you can get a negative. Can you get a negative? I think so. No, it has to be a completely different person. So anyway, for the process we're dealing with, we can imagine sort of a world that seems highly unclustered, and so you see very little density along the diagonal, to a world that's very clustered, you get very high density. And what we're trying to do is find a way to get that. Now, the reason that this is hard is because of the combinatorics. We don't know the number of groups. We don't know the assignment of people to groups. We have those two things to change. And just imagine how many ways I could assign one person to two groups, a population to two groups. Now take everyone, I can have one person in a group by themselves and n-1 people in the other. I can go to 2 to n-2, 3 to n-3. That's just for 2 groups. Now do it for 3 groups. You juggle them all around, do it for 4 groups. Like, this is just ginormous. If you want to do that, there is a routine in iGraph called cluster maximum, cluster optimal, cluster underscore optimal. It is there. It will do all possible combinations up to a size that you set. Don't do it on a graph bigger than like 7 nodes, because you will run out of time. Right? It won't work. So instead, what we've done, we cheat. We say instead of trying all possible combinations of nodes to edges, we try to find something smart, and we say, well, let's do something. We know that 2 people are tied to each other. They're more likely to be in the same group than 2 people that are not tied together. So let's exploit that kind of information to see if we can figure out if people are in the same group. And this has been your ticket to fame in the field for years, right? If you want your network badge, you invent a clustering method. And so there are lots of these methods. And there are a few sort of families of methods that I'll talk you through in a minute. The first set of families are agglomerative methods. And what these do is exactly what I hinted at there just a second ago. Let's start with nodes that are in different groups, or that are tied to each other, and say, well, they must be in the same cluster because they're strongly tied to each other. Then let's find the clusters that they're strongly tied to and so forth. And we end up with this nesting structure, this hierarchy of nodes that are really similar here, a little less similar here, a little less, and a little less. And this is a non-stupid thing to do, right? So this is a reasonable sort of first approximation of what you think the world looks like. Any idea what the main problem with this method would be? Just intuitively, what goes wrong with a model where you start at the bottom and work your way up?
First is where you draw the line. How do you know you fit the ideal solution?
When do you stop, right? So that's one problem. So we have a hierarchy. What else can go wrong?
Depending on where you start, you can end up with different results.
Yeah. What if I picked these 2 as my first start? Now I'm building on a mistake the whole time, right? So you got to pick your nodes that start really smart. The fast greedy algorithm is exactly this. You start at the bottom, it just goes up, it doesn't check for any mistakes, it just keeps going on. Drawing the line is a little bit easier if you have that heuristic, because then once I have the line, I can measure the heuristic here, I can measure the modularity here, I can measure each line, and just take the biggest, right? So you could do that. Turns out that's actually not a smart thing to do, but that's an easier problem to solve. The solution to the initial mismatch is what the Leiden and Louvain methods, respectively, have done. And so what these methods does is they say, let's do this process of agglomeration, wrong direction, in a backwards and forward set. So we go forward, we start here, we go up a step, we go up another step, then we go back and see was that first step the right one to do. And we move that window as we keep going. And it's clever. It was a clever solution to unwinding early mistakes so that you don't build on them quite as fast as they might otherwise. Once you have this, we need to think about this resolution parameter. Because it turns out that we end up having I'm going to come to this and I'm going to come back to this in a minute. Just remember that the problem with the resolution parameter is that the Q measure, it turns out, resolution is a tuning knob. It's a knob that lets you see small things if you have high resolution or big things if you have low resolution. It is, as Peter Mucha likes to say, your focusing knob on a microscope. If community detection is a microscope, this is how you focus. And it challenges this idea that there is a set of groups in the network. There might be, but it might also be that you have a hierarchical collection of groups. And any of us that have been in a university know that we have divisions, and nested within divisions are schools, nested within schools are departments, and within departments are factions, right? And so you have all of these different levels. Well, that's just a different focus. And so you might find across different levels of your resolution a solution that is relatively stable, where here I find departments and here I find divisions. And this is what this allows us to do. We have some tools for getting to that, what I'm going to get to at the end. So then how do we figure out some other algorithms? So if this building process is challenging, so the other common solution or heuristic is a divisive process. And so a divisive process says, let's start with the whole thing and cut it at its weakest link. Then take the next thing and cut it at its weakest link. The classic version of this is called edge betweenness. And so just like you can have the betweenness of a node, you can have the betweenness of an edge, and the betweenness of an edge is the number of shortest paths that go through that edge. And that edge is holding a lot of weight to hold this network together. So if we remove that edge and the thing falls apart, that's likely, right? So let's pull that one apart. Then we say, let's take the rest of it, find the strongest edge, fall out apart, find the next one, find the strongest edge, and fall out apart. There's some technical details about how you actually do that. You can't actually just weight all the edges, sort them, and remove them. You have to recalculate them each time, it turns out, for this to work right. So it's an expensive measure to do, but it works kind of nicely. There's a third version, which is I'm particularly fond of, particularly for social sciences, which is what I refer to as a process optimization model. It says, well, why do you care about these clusters? What is it these clusters are doing for you? Well, let's simulate that process on your network and identify nodes that are the same at the end of the process you're trying to do. And so a classic version of this is something like label propagation, where we'd say, let's just randomly label some nodes to start with, then diffuse that label to their neighbors, do that in a smart way over and over again, and nodes that share lots of labels should be in the same group, and nodes that share different labels should not be in the same group. Now, do that in a smart way is code for a bunch of detail I don't want to talk about right now, but just that's the way that's there. Now, another version of this is walk trap. It's the same kind of idea where things are, but in this case, instead of labels moving around, you have a random walker who keeps track of where they go. And if I revisit the same place over and over again, like if I'm just moving through this network and I keep 13 and 14 just keep bumping into each other, that's an indication that they should be in the same spot. This would be a good model for rumors moving through the network. So if we can imagine people spreading rumors in the network, it sort of circulates, people who know all the same stuff about everyone else in the community, that would be a good argument that they're in the know. Like I'm in the know with some people and not with others. Then there are a series of models, what you might refer to as either direct search or eigenvector-based methods. So direct search methods are where you've defined a certain particular pattern. You scan your data where you're trying to find that pattern. The best version of this that is no longer exists is Negapi. I mean, it still exists, but you got to boot up a Windows 95 sort of environment for it to work on. But it's a really clever program as part of the Multinet suite. It's fuzzy. You have to know how to play with its parameters. Eigenvector-based methods flip it around a little bit, and these are you can call them that, or you can these are effectively saying, Moody, your stupid network isn't that special. It's just a matrix. We have matrices. We've been dealing with matrices for years. So why don't we apply all the tools that we know from different sorts of sets of process, social process models, or social systems models, and think about things like factors in an eigenspace from psychometrics, or process optimization from control theory, and we can use these kinds of things to identify where the networks are. And the beauty of these models is that there's a whole bunch of statistical mechanics behind it that we already know. Let's see how that works. And finally, there's a third set of, or fourth, I think we are, set of approaches which come out of a tradition that are building largely on the eigenvector sort of set, which are known as stochastic block models. And the main thing about stochastic block models is stochastic block models are they're different in the sense that the end result of them, as we use them for community detection, doesn't seem that different from anything else we do. But they're qualitatively different in that they're proposed and written down as generative models. The stochastic block model is a hypothesis for what the world should look like, and it's conceived of as a data generating function. So if I have the stochastic block model, you think about how that generates the network, you can specify an arbitrarily complex stochastic block model. It turns out that specification allows us to think about a lot of things, and so that a lot of people like it, and there are ways you can deal with it. In practice, the type of stochastic block model we always estimate is a diagonal, heavy stochastic block model, may or may not be heterogeneous, and then it's estimated by some kind of an underlying sort of search process. And that's where it falls apart often. If you're willing to, some of these tools use a nice version of it, sort of the MCMC sort of set. Others that people have used are really just some of the other heuristics under the hood that are then tested on top of it. And a few others use sort of the same kind of edge flipping that we get out of the Ergom sort of package, which is why they're the same authors that are built in this. Now the battles begin. We've drawn the front lines. We know where they're at. It's time to go to war. This is the first casualty of our little skirmish, which is that you would think when you do the same thing to the same data that different methods should get there. So we all love triangulation. If you triangulate any of these different methods on the same network, you often get a different result. Sometimes that matters, and we care about having a different result. And so we would like to know whether or not one of these results is qualitatively better than one of the others, as opposed to just different. And to get a better sense of how, on that particular network, here we have the number of times each pair is put in the same community. And so there's some signal here, obviously, right? So this little cluster, this little cluster, this little cluster. But there was some method here that put these two together, at least once. Another method that put these two together at least once. And so it's a problem to think about a method that we applied not to a different sample of the same data, but to literally the exact same data and give you a different answer. That makes all of us just a little bit icky. So how do you do it? Which one should you pick? Well, there's lots of ways to think about this, and there's lots of arguments about it. This has always struck us as the right kind of a question for a Monte Carlo experiment, so that's what we did. The problem doing a Monte Carlo experiment is that we don't really have a gold standard to compare against, so we had to make up a gold standard to compare against. And we're not the first to do this. A lot of people have done this. The problem with most gold standards that people compare against is that they look exactly like this. Right? They look like the only information in the graph is that it's a diagonal block model with different densities. Real life doesn't look like that, so the sort of little trick in our set is that we generated a set of models here where we can vary the structure that's not relevant or shouldn't be relevant to the community detection. So we have some people that aren't in communities, we have some communities that are a lot bigger, we have communities that are nested inside of each other, things like this. And so we're attempting to generate networks that are a lot more realistic than they are others. We generate literally hundreds of thousands of these. We have some different divisions. We have some weighted networks, some unweighted networks, some that have short degree distributions and others that have not short degree distributions, that have something closer to a skewed, to a power law degree distribution with this kind of density, so it's hard to actually do. But we have lots and lots of them. So our mixing matrices look complicated because we think the real world is complicated. And when you go through and do this, you get these networks, you try to see what they look like. We tested it against, I don't remember, it was like 14 or 15 of these different methods. And I won't give you the details here, but you get this kind of a result. So for every kind of method you might do, we can then vary the signal, like how grouped is it, and then we can get the result of our Monte Carlo for a binary skewed network or a weighted skewed network, a binary random degree distribution or a weighted degree distribution, and you get different curves for each one. And the way you read this graph is this is what's known as the adjusted RAND statistic. A high value means that the two partitions match, in which case we found the right partition, and then if it's really low, you didn't find the right partition. So in this particular case, it looks like edge betweenness was not unreasonable for something like a binary Erdos graph that is a binary network where there were no stars, there were no hubs in the network. It has a monotonic relationship between the signal and the result. But once you try to add a skewed degree distribution, the edge betweenness model seems to fall apart completely. A lot of results. This is why my papers take so long to get out the door, because like, what the hell do you do with this? But what you could, I want you just to sort of step back and squint. And the thing I want you to see from this is the sheer amount of difference across these methods. There's lots and lots of partitions. You don't have the right partition or the wrong partition, the best partition. Sometimes, like this guy, for this particular structure of a network, the edge between this model does terrible, 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 terrible until the answer hits you between the eyes, and then it finds it perfectly, right? So it's like nothing, 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 nothing signal. Whereas the Leiden sweep method on the weak core, it's like it finds the right answer every time. Right? And so what's useful to think about in something like this, it's too many results. See, and then you have a whole other set of routines. So we have the those and those and those. So let's just put it in a regression at least somewhere. This is a descriptive regression to help us to see what we're seeing. And so what we find from this little exercise is that community, a signal does what it's supposed to do. That's just the design, right? So we find that when there's a weak community signal, it's harder to find than when there's a strong community signal. We find that in general, if you add some weighting to the network, what we're weighting by here is other group signals, so transitivity, reciprocity, things like that. When that's added to the network, you get a bit of a boost, which is good. These models do a much better job of fitting sort of a normal degree distribution as opposed to a skewed degree distribution. And there's high variability across both the type of methods and the type of networks and the type of methods. But if you know nothing else, like if your goal is I need to go out and find an answer, the two things that we learned is that the Leiden sweep method is very good, but this comes with an asterisk that I'm going to explain in a second. And where'd it go? Walk trap. Not walk trap. Infomap, there we are, sorry, Infomap. The process model Infomap does a really nice job. Now, these differ a little bit in their solution depending on which network they're being ran on. So there are interaction effects, if you will, between the different structures in the network. So some of these methods are better at finding nested groups than others. But if you know nothing and you need a quick answer, this is the way to go. Now, the problem. Whoa, that's not right. This is the wrong. That might have screen. This might be the wrong file. Please tell me I didn't delete all that. No. Is that the one that's on? Oh, it's not, I'm on the wrong year. That makes more sense. All right, sorry about that. So now let's go back to that Leiden sweep method. So the Leiden sweep method says that the resolution parameter that you're using in the network should matter because that's letting you focus on where the cluster is in the network. And so what we want to do is go through and try a bunch of different resolution parameters and then take the model the best. Now, the beauty of this method is that it is fine-tuned. It works really well. If I go through and search the parameter space, I can usually find the right answer if I know what the right answer is. That's not really fair, right? So this is why that answer comes with a big asterisk, because if we don't know what the answer is, then we can't get to it. So we need an alternative solution to this. And the solution to this is called CHAMP. And CHAMP is an algorithm that Peter Mucha and his colleagues have come up with that allow us to post-process the partitions of the network to identify where the groups are. And the reason this method works is because it turns out that if you calculate a bunch of partitions and compare where those partitions fit on the space of the resolution parameter by the quality function, and this is just a non-normalized version of modularity, it ends up always having this beautiful convex hull because each partition is part of a line that defines the set of partitions that could be in that set. And those overlap in various ways. Now that's a bunch of words. Moody, what are you talking about? What I'm talking about is that at any given resolution, this is as good as you can do. Modulo, you have a reasonably good starting set of partitions to start with. Moreover, it turns out that many of these partitions are identical because they fall on the same line. So you think they're different partitions, but they in fact match each other exactly. And so what you think is 1,000 different partitions are in fact a dozen different partitions that you need to look at. So this narrows the set of things you can look at. So what does that look like? What do I mean by that? So in that case, we've added this now to the IdeaNet software that we have developed. And so this is a built-in example that's coming out of the software we have there. This is what I was hoping to show y'all. This is a very small network. So this you would never do community detection on a network of, what is this, 20 nodes? Not even that. But it's reasonable to have a sense of what we're at. So this is the Florentine Families Network, for those of you that don't know it, where we've merged both the marriage and business edges just for kicks and giggles. And if you run this champ partition on it, what we're doing is we're saying, let's get a number of partitions on this network, and we're going to we're going to let the model find 500 different parameters. So there's some random noise to this, so we're finding 500 solutions. That's ridiculous. I mean, that's nonsense. You would never look for that many, and I'll show you why it doesn't really matter in a minute. So you run this. And then we say, let's get the unique set of those. And that's kind of nice because you can do this. And it generates this kind of a curve. And what does this curve tell us? This curve tells us that in fact, there are only 1, 2, 3, 4, 5, 6 unique partitions that have any sort of value, that are at the maximum of their possible solution space. And so already this number 500, 494 of those were duplicates, or they're down here in this space and are not worth looking at. So these are not things that would be good choices for us to use. This solution is the same solution you would find across this entire range of the focus of the resolution parameter. This is the solution. So the length of this line segment tells you effectively how stable it is with respect to that underlying resolution parameter. So whatever solution 5 is here, and we'll see that in a minute, you have to be dialed in exactly right to see that. Now that might be a solution you're interested in, probably not. So what do they look like? So the first solution that it found at the lowest resolution, and the lower the resolution, the smaller number of bigger groups you're going to find is down here. And this is a trivially stupid one, right? You have the isolate and you have the connected nodes. That has to be true. This is number 2, sort of breaks it into a little quintet up on the top and a few on the bottom. Number 3 splits that group up. And this is a little bit deceiving on the layout, because if you were to just rejuggle where this clique goes, these 3 would be next to that one, so you want to be a little careful about how you read that. But number 5 is sort of a cute sort of set there. Number 6 is there. Number 7, number 8. All right, now we're 8th in order. So as you move up the resolution parameter, you get better, you get smaller number of finer groups. So you get departments instead of divisions. And this is what the entire set looks like. So this is better than 500. So now you could, as an analyst, just look through those and say, all right, I think that, based on what I know about the world, this is a better solution than is this one. But it's still not the best. You can also do things like ask yourself whether or not, how these things compare over the time. One of the things that is sort of informative to novices that you might not appreciate is that these clusters aren't necessarily nested. That the best solution at this resolution parameter steals people from 2 groups and puts them in one. Right? So it has this kind of effect going on. So a little bit of more advice. It turns out that Mark Newman and some of his colleagues have approached this problem from a different direction. And there's an equivalence between a maximum likelihood function for a stochastic block model, and this is the advantage of the generative logic behind a stochastic block model, that the maximum likelihood function of a stochastic block model is equivalent to the partitions that for a particularly specified way of thinking about that stochastic block model is equivalent to the resolution parameters for any given partition. And what's nice about his solution, and he did it independent of the heuristic search set, he was entirely within the maximum likelihood framework. What he was able to show was that if you have a partition that is a little bit off, from where it needs to be, that there's in fact a hump in the maximum likelihood surface where you could sort of move to. And every given partition has an optimal resolution for that partition. And if you find you find a partition at the wrong resolution, you can say where it should be moved to, then you can go to that resolution and identify perhaps a better partition that fits at that resolution. So what that in fact it effectively implies is that this second partition wants to be right here, which you'll notice is in the middle of its observed range. These partitions want to be right here, and the blue partition is in its range. I find it easier to look at networks as networks as opposed to on this. So this is a version of that. This is the exact same graph, just without the information on the axes, which is a lot of information to lose. But the important point is you'll see that the second cluster here is self-referenced and the seventh cluster is self-referenced. So what that means is that in this space of where a partition wants to be, these guys are happy. These guys are not happy. They don't want to be there. They want to be somewhere else. And so this now narrows our search for what we need to explore to 2 partitions. So we went from 500 down to 2, and these are them. And so neither of these partitions are inherently better or worse than the other. They're different partitions that at this different resolution, this different focus level. One has 3 groups, the other has 4 groups. And you can decide as an analyst whether or not splitting up this little group around 8 on this set is a sensible solution or not. Right? That's a substantive question. And that's what's there. Now, again, it's trivial on a network at this point. That's just for illustrations. There's another version in the lab that you can play with, which is football divisions, college football. And those of you in the room who know me know that me talking about college football is like ridiculous, but I'm not even sure which sport this is. I can't remember what kind of racket they use or anything, but in any event, apparently sports teams play each other. In the process of playing each other, they do things like win or lose. And historically, there have been divisions in college of football playing. And we can ask ourselves, based on how often this win-loss playing record works for each other, what kind of communities we can detect. And you get this kind of surface. Now, the problem with this kind of surface is that as an analyst, this is a lot more than 6, right? So if I'm asking you to go through and say, just try each one and look at it, isn't going to be very effective. Instead, we can use this mapping point to then say, well, where do these partitions want to be? And it turns out that there's one big partition they all want to be, and that apparently, historically, is the division, or very close to the divisions that we know ground truth. So this is the college divisions in the Big Ten and all that kind of stuff. Is Big Ten a word? Is that the right word? So Pac-10, Big Ten, something like that. So in any event, you have these groups actually match, and so it's akin to a ground truth in being able to find these sets. I think it's a nice pipeline to work with. And the good news is that the work required to do it for you is really just that. You pull it into NetWrite, and then you drop a couple sets, and you identify where your groups are. Now, an important thing to notice on this is that we, under the hood, for the 500 we just pulled in this one, are using Leiden. You can use any solution you want. This is a post-processing algorithm. So there, you can use, if you have another algorithm you want to use, go for it. The beauty of this mathematical sort of truism that defines this curve is that it doesn't matter where your partition came from. Any partition can't be here. Like that's a mathematical impossibility. You might find a better set somewhere because of this algorithm. Logically, it's possible that you missed some really informative case, and so this curve would be here instead of here. But there's none of our methods are so bad that you're going to miss something up here, right? And so the beauty of that is that it really takes the which method should I use algorithm away and says, if your method is, you can either use a really expensive, slow method and find a small number of solutions that are probably in this space, or you can use a really cheap method and do a lot of it and still find the set of solutions here, but find a lot of noise that's down here. Either way, this post-processing routine lets you find the solutions that are on that set. And that's where the strength comes in. And once you have those, then you can narrow the field to figure out which of those are worth your time as an analyst to spend some time looking at. Makes sense. I know that those of you who haven't been fighting in Afghanistan for the last 20 years don't realize what a godsend this is. But this is kind of a big deal. Please.
Just want to say this is like absolutely wonderful because independently I was using the Latin algorithm, but doing the manual sweep and finding a very fine-grained set by modifying that resolution parameter. Then I stumbled on the question, great, how do I optimize these, or how do I know which ones are most important, right? I looked at consistency, but I wasn't very robust. I was just like, okay, this set appears more often than all these others. Maybe that's a stable solution. So yeah, when you showed all this, I was just like, oh, there it is, fantastic, right? This is something I've been running into.
And you don't have to, like, again, I'm a pictures kind of guy, so I like sort of having these, but it literally tells you in the output of your window, partition number 2 and partition number 7 are the fixed point on the graph. Look at those. Right? So for those of you that don't like to look at pictures and do sort of in-depth exploration of that, you can just look at it and see what's there. Now, if it were me looking at the high school network, or this one network, for example, I want to know what 31 is. I would go, now, if I cared about football, I would go. All right. In the last 10 minutes, and then I'll let us get some lunch. No, we don't have lunch today. We have the, sorry, we're not feeding you today. That was rude. I apologize. Just to point out that the alternative way of thinking about clustering a network is roles. And because I can't spend all day on it, I'm not going to spend hardly any time on it, because roles are incredibly interesting and important. From our standpoint, the key is, remember, that we're trying to find from the data this kind of a partitioning of people into parents and children or whatever role is going on in your network. But at the end of the day, this is community detection on a similarity matrix as opposed to community detection on a network. And so there's some complication, and the trick is particularly in defining what counts as similar. And so it's similar in respect to what, and I want to spend just a minute here describing what that is and what the flavors of these things are. But the way it fundamentally works is that you have your different sets of relations, you combine them in a non-stupid way, and you ask how similar they are. And so in this case, I have parents, they feed children, children bicker with each other, parents love each other in a way they don't love their kids. And so you have that kind of set of relations. We figure out just pairwise whether they match. So this is a very simple structural equivalence measure. And we can then see how similar they are. And the worst cluster analysis community detection tool in the world will find those clusters, right? So that's because it's a toy example. Real world is different. Now, the fun of this kind of work comes in defining the different kinds of equivalence. And so structural equivalence, theoretically, you have same ties to the same to the same people, the same exact people. So structural equivalence is inherently a combination of modular groups and positions, because you have to be tied to the same people. There are special cases when that won't happen, but by and large, structural equivalents are going to give you sort of clusters that have some element of cohesion built into them, usually with a group that's isolated, sparse, or something like that. Automorphic equivalence means you have the same pattern of ties to all others in the networks. Nodes are indistinguishable on any summary metric. So if I have a set of nodes that have a particular profile of degree, then this nodes in the same class should have that. Regular equivalents are the same types of ties to similar types of people. The idea here is that we don't have to have the same metrics. The same metric isn't quite right, but the kinds of people we're engaged to are the same. Role equivalence is some ugly mush of these two that, again, in practice works because, given the noise in most real data, the defined distinctions between these are really hard to do. Regular equivalence is theoretically amongst the most interesting because we can think about things of doctors and nurses in small hospitals and big hospitals shouldn't have the exact same summary metric, but doctors answer to nurses and nurses answer to doctors in the same way in different sized places, so that should be something we should be able to find. The sort of standard measure for doing this is a tool called Reg-A that was developed by White and Ritz, right? Yeah. And it's hard. And so I'm just going to say we're working on some new tools to try to get in that direction from the role equivalence we're getting out of triads. So there's some extensions we're moving on to this, but it's just a very difficult thing to get. So what does this look like? If you were to do the classic measure of structural equivalence is Concore. And Concore is a really old-fashioned sort of model that works by magic. The magic of this work is that if you take any kind of correlation matrix, and this is the case is what I've done here, is I've taken this network and I've correlated the first column's values with the second column's values, the first to the third, and so forth. So I turn this adjacency matrix into a correlation matrix. If your underlying network is directed, then I've stacked the observed matrix on top of its transpose, so I can get both ties sent and ties received. And so anyway, you've converted this to a similarity matrix. In this case, literally simple Pearson correlations. And the magic is that if I then do that same trick with the correlation matrix, I get a new set of correlations, and again, and again. And by magic, you always get positive ones and negative ones. That's the beauty. The concore will converge, probably with some asterisks, but in practice it will converge to only positive ones and negative ones. And then you can divide your network by this. So that gives you your first split. And then you can go down these different branches, and all the magic here happens, so the mathematical magic is in that necessary convergence of correlations, and that's what the algorithm means. So concore is a convergence of iterated correlations. But the splitting of it is where the qualitative sort of judgment comes in. So do I stop at 2? Do I only take at this set, or do I go deeper in one branch or another? You as an analyst have the freedom to figure that out. This is what we did to get our political polarization graph. And so what we thought, Peter Muka and I did this work too many years ago now, we thought, well, there has to be something like party loyalists and bridges. Let's just block model it and see what we find. And you always find party loyalists, and you find some division of people who are not party loyalists. And so sometimes it's really interesting when the world is interesting, and you get within party divisions. Right? But most of the time you have one big group of good soldiers that do what they say, some people who are willing to stick their necks out and do something else, and the number of people who are willing to stick their necks out and do something else have decreased over time. Right? So this is a very nice way of getting at this. You'll notice this stopped about 10 years ago now, 12 years ago now, so I suspect that even finding a few people here in the middle now would be next to impossible. But that's, so then you can interrogate things like this and see where it comes from. I've always used role equivalence as the alternative to concore. So if you want to find something where people are in similar patterns of ties to similar others, and they don't have the restriction to being tied to the same people, similarity based on your vector of relations on triads is a pretty clever trick. I wish I had thought of it first. It's that kind of a trick. And so what you do, just because I went over it so fast before, you didn't have a chance to actually see it, is that each of these little social elements, right, that we are now as they're boxed, have within them positions. And so within this smaller scale of being, in an empty triad, we're all the same. We're all alone together in the same way here. Whereas in this cute little triad where you have one mutual tie, that's where an asymmetric tie is tied to it, you can either be the person who loves everyone, you can be the person who's receiving all the ties, or the person who's a mutual outsider. And so you have each of these different kind of positions within this one type of triad. And so you can just count that up. Counting and sorting, that's what network analysis is. And so once I count that up, I can see that A and B have the same pattern, C, D, E, and F always have the same pattern, and these guys at the end all have the same pattern. And so again, then it becomes the same sort of process. I have a similarity matrix, and I find the clusters on it, and you get your, in this case, you get levels of the hierarchy. Now it turns out that triads are a great piece for this, but they're limited to a diameter of 2. And so you need to often add a little bit more of information to it. And if you think about this in terms of any summary statistic, you can add things like your closeness centrality, for example, to get to whether you're at the edge of the network or the middle, which community you're a member of, if you wanted to get at something like the positions of groups going on. So there's lots of different things you can add, and that's the direction that this work is going. There's also a way to do exactly this trick where we say, which one are you in? This now becomes a 2-mode network, where I have how often do I send to each of these types of ties or receive from each of these types of configurations, and you can spread that out for a long way. So you can spread out the connected to patternsness to get a little more fine-grained. The good news is, again, IDNet does this. We have this under the hood for you. Learn an IDNet, you go through role analysis, and you get an entire description of where things are at. You can either do it in the, I thought I had it here, you can either do it in the structural equivalence model through Concore, so we have that built in, or you can do it through the role analysis, where we have the triad distribution, where we add a little bit of extra centrality to it just to help situate nodes within sets. Again, I knew I would talk too long, so I didn't even give myself the slides to show you how to walk through this, but that's there. So I promised to say, I started this off by saying I wasted an hour of your time talking about something I'm telling you not to do. So what should you do instead? Right? So we care about groups. I think that if you care about groups because you care about similarity, because you think they're the same, then measure similarity directly and do a model dyad difference, for example. So I could say, how similar are Carter and I in terms of the third people we co-author, and does that differ from how Carol and I, the people we co-authorship? I can do that as a dyadic regression. It becomes an edge covariate on something else that we're doing. And so if your problem can be recast as a distance problem or a similarity problem or a matching problem on a lower level, you can sidestep a lot of these problems. So think a little bit carefully about that. On the other hand, it is fun to have groups. We like groups for sociologists. And then once you get them, you can use that as a way to condition a lot of these other features. So if you're running an ergom, or if you're running some other kind of a model, you might expect that reciprocity is higher in one cluster than another. You might expect that centrality has a different effect on behavior within one cluster than another. So there are reasons why you would think this would matter. And in that case, you actually need the labels. And so you may as well try to find a good label. And I'll stop there. Questions or comments? Thoughts, concerns?
Just to double check, that's on CRAN, good
Yes,
documentation, fantastic.
everything's on CRAN. Including some really remarkable vignettes that Tom put together for the role analysis. My brain's started farting out on me now. And Peter put together 3 different separate vignettes for the cluster analysis, for the community detection. We discovered in the process of doing this that you can't have them be one big vignette. It takes too long to run, and CRAN kicks you out, which is really frustrating. But we were able to get that fixed.
Thanks.
Any other questions? Gabe?
Since we're talking about this, other people are asking me to do it. There is also functions for fluid analysis. These are all points.
James reminding us that there's also similar functions both in NetWrite for all the analysis we're doing here, plus some of these other things for ego networks. So we are expanding the entire tool to be to do descriptive analysis on ego networks. So you'll have that as well. What's that?
That those are all under the same roof.
Yeah. And the reason it's called IdeaNet, for those of you that know, it's integrative data exchange. And so the goal, ultimately, is to make this, there's an API under the hood to allow you to link to data in repositories. That's the big promise eventually. We're having some truly just bureaucratic problems with that our universities won't play nicely with us to make that happen. But we're,
Carter's thing about systemic policy.
yes, exactly. So once we figure out how to get out of that particular morass, and which we have solutions for, then there'll be ways to do that as well. All right. Again, I apologize for having long slides. We're going to end today with just an open session of new directions and future directions. And I have a handful here that I can walk through. I don't want this to be anything more than a seed for ideas to sort of think through some pieces in this last half hour we have together. But I really want and I would love to, you've heard a lot from me this week and a lot from me today. But if you can, and so I would love to hear what other people in the room think are the most important problems and where to go next. But I'm going to give you my first, at least, broad areas that I think are worth thinking about, and then we can move forward from there. So the first sort of broad domain, I think, this is coming straight out of the book that Craig and I wrote, so this is not my ideas, it's our ideas, which is going big. Scale is still an issue. There's network analysis has traditionally been case studies or multiple case studies, and it's been amenable to this intellectual approach of interrogating your data, learning your data, thinking carefully about your data, making fine distinctions. That's hard to do with millions of nodes. And so I think that the scaling up question is really a theory question and a methods question. Good night, folks. Thank you. And yeah, leave if you have to. There are planes to catch that are much more important than my rambling. So the scale issue, I think the question the question everyone asks about scale, I think, is the wrong question about scale. The question everyone asks about scale is, can I run my big network data through your small network tool? Maybe. Sometimes you can. The real question is, why would you? Right? What are you actually going to learn from studying, from a model that's built on billions of nodes that you couldn't learn better from a model built on 100 small parts of that network? Does the social process, that many of the social processes about communities and groups and so forth have built under the social theory behind social cohesion, for example, is some kind of a horizon of visibility that I can know of others and be aware of where they sit? Is that feasible in your setting? Does it matter for your setting? Right? Does it change what you're doing? And so you need to think a little bit carefully for that. And I think that there's a lot of good work to be done in situations where scaling does matter. And so certainly for disease diffusion, the virus doesn't care if it's a small community or a big community. So there, the size, of big networks probably would matter. If I could have the actual disease network of an entire country, that might be very useful. But for community things, it might not matter as much, right? So we want to think about that. The second question that I think is open is this, what we call is going deep. Right? So we can go big, we can go deep, which is that real-time traces produce these micro-level sort of elements of data that are deep insights into what people are doing. So if you think about the digital traces that all the stuff we were able to learn from during the COVID era from SafeGraph and other things where you're following people around. There was a wonderful paper that just came out last semester, because I immediately jumped on it, just drawing a blank now, on downstream effects. It's in sociological science, on downstream effects, economic effects of people's movements. And so if I know where people go and they stop going there, what does that do to the businesses that are at those places? And so you can actually figure out which kinds of places are dependent on economically and which other kinds of places by the fact that people go to those places in sequence. And so there's lots of beautiful data that comes out of where people spend their days, and I think that's worth doing. I think that there are digital versions of that, and there's also sort of cognitive versions of this, which is, are we living in, this is what I put under the hood of, are we living in the same network? So we're in the same space, we're talking to the same people, but do I have any perception of this that looks anything like your perception of this? This was the beauty of the cognitive social structures literature, and that literature is just, from a behavioral standpoint and understanding standpoint, I think is really untapped. It has been underused. I would love, for example, to go into a hospital and see, well, what does the social process look like in the nurses, the orderlies, and the doctors, and what do they actually see there? And I suspect that they see something very different relationally, from both power standpoints and behavior standpoints, and probably risk standpoints. If we care about health and disease, nurses sort of see a flow of risk that's very different from what doctors probably see. I think that there's a whole literature that we haven't touched in this work, and this has been my failing because I haven't reached out to them, but there's an entire community of people who do small group processes. And the small group processes and the network people do overlap, but they don't overlap with the networks and health work as much as they could. They're much more in the organizational side of things, and I think there's a lot of work that can happen in small group processes and functioning in organizational systems and responsiveness to organizational innovations. I think we can go really deep into diffusion, right? So does the trip change the traveler, right? Is it the case that what I'm engaged in and what's moving through change what it means to do that again? So, there's some old ideas about this, but I think there's lots of sort of ethnographic sensibility that we can apply to either trace data or individual data that allows us to sort of follow some of these processes. This is where I live, and so this is my bias in this set. This is the comparing structures in the middle. The biggest, I think, there's certain methodological advantages, but the biggest data advance in the last 40 years, 50 years of social network analysis has been the ability to have multiple networks. And so instead of doing a single case study, an N of 1 case study, we have able to do at least a small N comparative study where we have 200 high schools. 200 high schools is amazing, right? When you compare the amount of work it took to do one N. So I think living in the middle there, it turns out that we have lots of opportunities to do this work. We can do it by sharing data and by collecting and making sure that our data are comparable in various and sundry ways. And this is why I am, well, perhaps not optimistic, very sympathetic to Neil's goal of making sure that our data are comparable, that we are collecting things that are into it. And we have a lot of this work that's happening right now. Myself and Dana, she's here, we have a grant that is hopefully someday going to get funded or refunded. It was just, anyway, there's a, where we have at this moment collected network data from 25 different projects comprising over 2,000 villages and touching over 20 million people, time combinations. And that's just data that's truly freely out there in the world. And this is because every one of us in our own world has gone out and collected some of these data. We might have a village sample of one set or the other. And in the process of doing that, we answered one question and put the data somewhere and then forgot about it. But collectively, that's a lot of data in the middle range to allow us to do comparisons of one thing to the next. And I think that if we look just a little bit, we'll see this. The other way to do this, which I thought I had in this set, which is that I think there should be a return, yes, I have it under the data set down there, a return to community studies. This is the 100th anniversary this year, or next is the 100th anniversary of the first Milltown study. There was a proposal at NSF by the people at the university to redo Milltown 100 years later, Milltown at 100. It fell apart for various sort of funding and organizational reasons. But other sciences take as their starting point fixed, strong investments in fixed field sites. And you go back and you study Jane Goodall's chimps over and over and over again, or the elephants in the Serengeti over and over and over again. And you have people that do it, and you have a commitment as a field to studying a community and using that as an informative observation. And I think that there's some logic to that. In the current funding environment, probably not. But I think we should aspire to more to that, because this funding environment is going to change over the course of your career. And imagine what could happen if we had 50 years of continuous observation of a particular community, of the kids going through it, getting sick, dying, their parents moving in, moving out. Like these kinds of things would be a data trove that would inform an entire system in the same way that, you know, the Large Hadron Telescope or something does for everyone else. So I think there are ways in which we can think about communities not as little case studies that are kind of cute and fun to read, but as resources for the entire community to become a data investment for all of us to use. It's hard to do that with a big city. So the concomitant feature of this is we need more work on network sampling. And I think from a data collection standpoint, that's where I would like to see my work done. Finally, I think there's a final big challenge that's the obvious elephant in the room, and literally the group downstairs this whole week that we've been working and talking about networks, they've been downstairs talking about AI. So these have literally been two separate worlds talking at the exact same time, not more than 50 meters apart, but in entirely separate worlds. Do we get Hal, right? My chat, I'm very kind to my chatbot. I love him, I speak, you know, we have a relationship. So when they take over, hopefully you'll think kindly of me. But this is an entirely unknown world. I think the promises are really, really, really interesting. I think to the extent that it helps us get rid of some of the drudgery and do some things that are substantive, that's awesome. Remember that little guy pushing the ball up the hill? He didn't have a chatbot helping him, right? And then you learn a lot about the shape of the boulder by pushing it up the hill. And so there's a risk of a lot being lost. And so whether or not this is a net gain or a net benefit is something we're all experiencing in real time, but I think it's something worth thinking about. And so those are the ideas I had, which again are worth whatever they're worth. But I will then stop there and open the floor. Anybody wants to say anything else? Greg, what do you see in the next? What are your hopes and fears for the future of network analysis?
I think, like you, I think that, you know, a lot of us got into this to care about people, and as opportunities for developing more advanced skills get good and better, and we don't lose sight of that we're trying to make people's lives better and by trying to understand people fundamentally. So I think sometimes we get the cart before the horse. I think the horse has always got to be our love for people and our trying to make people's lives better, more peaceful, more prosperous. So I think there's always been a tension in science, and but I feel that that's maybe even more so the case today, especially as we are living in a world that is so driven by side hating, and we seem to be structurally equivalently all put in one side. So maybe that'll create more cohesion on our behalf.
Please.
To sort of hark back on a question or some musings earlier about the rapid advancement of things like online social networks, the sheer magnitude and size of these things developing and technology changing so rapidly. It seems that AI, machine learning advancements, especially with graph embeddings or graph neural network architectures, are these like complementary tools to start dissecting in very near real time the patterns that are unfolding and those realities, those worlds converging in these online spaces. What I think and what we're seeing where the lag is that the scholastic element, the understanding that can be derived from these pattern recognition tools is delayed. But I think, that can catch up, right? The tools and these methods are, fast developing. Calculus is useful, who knew, right? Turns out though, there can be understanding that can be derived from that. It's just taking the scientific community a little longer to figure out exactly how to translate that back to what it means about human behavior, human psychology, and human connectivity ultimately. But I think we're starting to see some really clever people and some really clever research groups finding ways to disentangle, right? The numbers, the connections, the patterns emerging from these models in very interesting, clever ways that do inform something about us and our processes and our social processes. But again, like you were mentioning, right? Science is slow. It takes time. It takes consensus. It takes understanding or unpacking of things to fully understand. And our brains only work so quickly, right? But it seems very promising, right? The landscape, it's rapidly changing, but humans are creative, and I'm seeing a lot of creative ways that we are diving deeper into these rapidly changing landscapes.
Please. Yeah.
Oh, sorry.
Was that a hand? I thought it was a hand.
Yeah, sorry. My brain is starting to fizzle out slowly, but that's the main thing that I'm trying to obviously I'm a third-year PhD student, and the answers tend to escape me more than I have them, but that's what I'm trying to do is trying to merge, especially what I'm seeing from my peers in computer science, what they're doing with AI and language learning models, with combining some of the stuff that my peers in psychology are using with what my peers in computer science are using in order to take these very, very large amounts of data that perhaps I would get from data donations and help maybe find patterns. Maybe I will find patterns. I don't know what it means, but I'm excited to find out.
Please.
I don't know if it's related or not, but it feels like you're illicitly thinking in it. It's something that I feel like open problems. How do we actually get some of this knowledge to communities? I think that, like we say, we're all motivated by open community, but we tend to do to communities versus working with community in the solution development and these theories that we have about protocol and community dysfunction. So I've been really thinking about how do we make these science more accessible, not just open science to people in academia, but actually working more on that translational sciences, so it gets to communities in the ways that they will be able to activate this knowledge to actually create solutions that are local, that may be at that meso level, that are also systemic levels. So we just published a paper with Jimmy Adams, my advisor on social capital, and it was really inspired with me going to, like, he having all of these ideas about social capital and me coming with the question, like, what the heck is social capital? Because all of these philanthropy people I work a lot with grants and nonprofit stuff, and they were all talking about social capital, and I was like, I have no idea what you're saying when you're saying that, right? So that's what that conversation started. After 2 years, we have a big paper, I recommend it all, that kind of dissects what do we need. And for me, that question is, now I have the paper, and I go back to the philanthropy people, and they're like, it's 20 pages, and it's extremely complicated. So now I'm writing another version, 2 pages. So people in community can use this knowledge for something that they value. That's not just this developmental, the development of this theory, or that the tools to do research, but actually the tools to communicate and make something for the people who need this help right now. So that's what I'm saying as an open problem, is how do we make science available to the scientific community, but also to the people who are having those issues, and that may actually inform what we do and bring more connections.
Lynn, were you? I thought you were, you know. Please.
I was going to add to that, really. I was in the RCR course, but we were talking about ethics and things like that, and I think that not sharing data and not having that, it also doesn't benefit us as well. It's not, we're violating a lot of the rules of social exchange theory, and we're kind of getting the short of the stick at this point in terms of like the viability of the film moving forward. Like, how are we going to ask for the public to continue funding science and believe the evidence? They don't understand the importance of it. And so it actually is our due diligence. It's not just only that, but if you're not motivated by that, then be motivated by the fact that you want someone to be able to have grants and continue to do the research and get the funding to do it. Because right now, there are ideas that it's not worth funding. It doesn't matter if this doesn't exist. This enterprise doesn't exist because it doesn't benefit me. And I think that there is this communication breakdown and this understanding. And to that, it is possible. It is incredibly hard. It's incredibly hard to break things down in plain language. But I had a crash course in my dissertation. I had no money. I had hardly no money, like $20 to recruit 234 trans women. That's after the data was clean, and do multiplex networks, programming Qualtrics. And so I had nothing but like grit and determination, and I also wanted to make sure that my population was representative of what we see in the HIV distribution. So I oversampled Black women, transgender women, and Black transgender women from settings in the Atlanta area. Not perfect, I didn't like get to different places, but that required me like going out and making sales pitches to community organizations and saying, I don't have any grant funding, but like how can this data about like the support, how support influences ART, which is medication, patient medication adherence, how can this help inform your client programming that you do? You have a lot of support programs. How do you know that you're applying like the right? So I did like House and Umberson support functions and program that in the egocentric, and we could see like what deficits there were and how those might relate to medication adherence. And these are the ones that you really want to focus on, the types of support. And like, cross-sectional, it's not the best, but this is the part where I almost fell off the cliff. Like I almost like jumped out the window. Like it was hard because like I defended my dissertation on Tuesday, and they're asked as to how do you want this data? Because it's not always in the paper. It's that we rely on grant funding as a nonprofit. I want to be able, and I also want you to come in person. We have a symposium. The symposium was 2 days after my defense. So I was like, not only am I in a room and I'm defending this and I'm talking about multiplexity, I'm using all these measures, these metrics, and I feel like a real science I pass, and then like I have to literally turn around with an audience of healthcare providers, social workers, and transgender women clients and try to talk about the research in a plain language. So ties became relationships. Networks became social circles. They're not like, it's not what we call communities like you did community protection, but like to them, like that makes sense to them. And yeah, so I got a really a big crash course on that, and of course I crashed. So like weeks after that, I was asking my friends, like, am I okay? Because I just want to sleep. It was really, really hard, but it is possible, and I think that if we want the science to survive, not only so that we can explore the things we want to explore and do the things that like really pique our interest, we have to demonstrate and find a way to continue to do that.
Yeah, if I may go right off that point, I think what you said about the crash course and like learning how to effectively communicate with various partners, not just for writing, scientific papers and disseminating it to the academic audience, but relating it back to your community, back to your stakeholders, back to the people you are serving by doing this research. That's a skill that we all have to learn as storytellers, right? We may use data to tell a compelling story. We may have to word that story differently depending on the audience, but it behooves us to learn multiple ways to tell that story to be the most impactful we can be, to serve those who fund us as well as those who are in need of the funding most accurately, right?
I would I think these are yes. I'm going to say it's a both and. The community is, and I'm going to put a plug in for science sake. The ivory tower, isolated from the world on its own, is in fact of value in itself, because that's the only place you get the calculus to get to the machines, to get you to the rest of these pieces. And so the investment in science for the purpose of science, the investment of the creation of knowledge for the consumption of all the other knowledge creators, that is in fact itself a value that we have to have. Otherwise, we're just journalists. We're just doing reporting. You have to have the foundation that built in. And this is why science and the community of science needs a division of labor and a division of skills. Because some of us are really good at talking to other people, and some of us are not. And I think that for a dissertation and for a project like this, then you jumped in and you did it. And I have a feeling that you're probably a lot better at it than you're giving us a hint at that you have, because otherwise they wouldn't have talked to you in the first place. But I think that there is a sense in which that kind of a trade-off of the project of whether we have an immediate return versus a long-term horizon is, in fact, it's like Granovetter's threshold models. That the system only works if there's a smooth distribution of those thresholds, and the science only functions if there's a wide range of investments in the modalities of doing interrogative intellectual work. For network science, the beauty of this is because it's been so interdisciplinary for such a long time, that we have the advantage of having networks of chemicals, networks of forces, networks of people, networks of animals. All of these fields have come together, and we've been able to exploit in many ways the intellectual efforts of all those people prior to that. And I think that then we can say, well, how is that useful on the ground for this community or that community or that community? That's great. And the reason we can do that work and do it at all effective is because Frank Harari figured out that there was an equivalence between path structures and node connectivity in abstract graphs without ever talking to anybody but the guy who needed to sharpen his pencil. So so I think that we have to remember that science is a collective endeavor, and that we are engaged in it in each of our spot because we all have a common enemy, or friend, which is Mother Nature. Like, nature is the thing with the nut we're trying to crack. We're trying to figure out what the world is like. And then, if we don't like the way the world is, perhaps we'll change it. But we want to change it in ways that are informed by knowledge and understanding. So this is why these things have to be working in what's it called, in sequence and in cycle. Please, Christina.
I think that there is a way to kind of compromise and at least increase accessibility. I don't know the name of the person at the top of my head right now, but there was a researcher that I saw once, when I was looking for a job, and he had gotten a grant to make his research more accessible. So he recorded 5 to 10 minutes videos, talking about his research, in a
like right now science is under attack, right? Like we have major forces who are, and in some ways we have made these are our own by having that relationship maybe with communities that's quite kind of polarizing or influence. So I think that it comes, it's a commitment, maybe a skill development, maybe not everybody can do it, but some of us have to do it, in which we can get closer to people so they know we care enough about what we care about, that they will be standing on the funding or ability or right or love for science. Otherwise, eventually it's not going to be supported in the way that has been supported in the past. I mean, we're going by that. So I think that these conversations are really relevant.
Please.
I think, I really appreciate this, because I mean, I totally agree that we need people in the ivory tower, like that's how we get to these incredible things that we have. Like, IdeaNet is an incredible innovation, but so like I've said this a few times, I'm interdisciplinary because I'm in urban planning and public health. In urban planning, like, you need to have someone in the room who knows how to do infrastructural network analysis. They're not researchers, they're not doing any research, but thanks to some incredible network analysis research and graph theory, practitioners have that knowledge, and I don't think we really have that level of investment in public health like I wish we did. And now that we have things like IdeaNet, I would love anytime you have a community planning intervention going on, someone brings the network and just puts it up on the board and we talk about it. Like, there are some papers that do this work, and unfortunately you read them. This is like I've done exactly one peer review in my life. They didn't really know what they were doing. It was a really cool project, and they sat down with their PTA, the Parent Teacher Association. They put the teacher network up on the board, and they looked at it, they talked about it, and they planned their like fundraising or whatever. And it was really cool, and this visualization was really cool, and it took them somewhere cool. But these were not necessarily people with a lot of kind of stringent knowledge of how it works, and they didn't necessarily need to have it. But I'd like to see that integration more like practitioners who just have the very fundamental skills that we are enabled through things like IdeaNet.
No, absolutely. Please. All right. It's been a long time. I've kept you, I've fed you, I've kept you away from your friends and family. Now I'm starving you and stressing you. I think I've hit most of the stages of becoming a member of our cult. So welcome to the fold. Your job now at the end of the conversion process is to proselytize. So this works about right. So find your way out. If we've learned anything from the history of proselytization, go in pairs. It's the only way to reinforce your own safety and rightness. Otherwise, you'll get overswamped by the heterodox out there. But thank you for your attention. Thank you for doing all this. Stay in touch. Again, big thank you to IID. Big thank you to all the RAs. Big thank you to all your peers. If you haven't made a new friend here, you still have 20 minutes to do so before your plane leaves. So do so. And in the meantime, thank you all, and we'll see you hopefully soon. Oh yes, we have evaluations that we have been lax filling out. Please remember your own sort of ex post evaluations and go back and evaluate the workshop. Thank you.